space environment is harsh, ionizing radiation affects not only externally, but also internally the critical components in the spacecraft, and also material, clothing, biological cells, solar panels, and so on. It can lead, if not properly thought about and designed for, it can lead to total failure of mission or partial failures. Not being able to meet availability requirements, reliability requirements, and then we will discuss a little bit about that. And obviously, as you all know, repairs are not yet possible in space. So we want a high reliable system. And that's it. And also, there is one important point is that this field is still an ongoing field. You know, part of our work is also to attend conferences in radiation to understand, because why? The radiation environment is the same, but the components are changing. The components are evolving. Now we have more and more integrated components. So some issues will result in the tendency of having less problems, and some other effects will increase. So for example, as a general, it's just a general comment, but more and more you have components that are integrated. They have the tendency to be less sensitive to total ionizing dose, but increased sensitivity of single event effects. But you know, you have not only a planar, CMOS, now you have FinFETs, and in the future, gate all around, and so on. So we need to understand how radiation affects these new technologies. So it's an ongoing field also, in particular with all these components evolving so fast. So my main message here is radiation-induced failure of a component, even temporary, so for one single component, can have huge consequences on the overall mission if you don't think about it ahead. So what is radiation hardness assurance? Here, we mentioned this a bit in the morning. That's one of our Bible. It's the ECSS standard QST 6015. Q because it's in the quality branch. 6015 refers to this radiation hardness triple E component. So first of all, radiation hardness is a PA discipline. But one important message I will discuss later in the presentation is that even if it's a PA discipline, it's very closely linked to the design of your satellite. And that's important. So it's very closely linked to engineering, okay? And I extracted this from the ECSS, the definition of RHA. So RHA consists of all activities undertaken to ensure that the electronics and materials of a space system perform to their design specification after exposure to the space environment. So the main point I've highlighted, but it's all the activities. And you know, some people, when they don't know, they think, RHA is testing. It's not only that. And I will explain a bit in the presentation. So basically, it deals with many different things. Radiation environment, defining requirements, radiation requirements, spacecraft layout, radiation, thinking about how to make the design tolerant, part selection, as we saw also this morning, radiation testing. And all this, you see, there are some loops. We will discuss about that. So that's also one important message I wanted to convey to you that sometimes is overlooked, and I will try to say that. But it's all about risk at the end of the day. And if this is properly understood, then it makes life easier in terms of how to do what you need to do in terms of RHA. So first, we start by the RHA plan, which is defined in the PA plan with some additional requirements. So all this defines what are going to be the RHA activities, to what level we need to test, to analyze, what are the parts that are sensitive, what we assume are sensitive to what effects and so on. So all this is defined there in terms of requirement. But to define all this, you need to have a good perception of how much risk you want to take in your project. Because it depends. It depends on your mission. It depends on your requirements. It depends on the criticality that you're willing to take, the risk that you're willing to take. And you need, so that's why you need to consider this at the very beginning, because this will drive the level of RHA that you will want to then do. Obviously, for this, you need to have a good knowledge of what is radiation, how it impacts components, how it can affect your mission based on your particular design, in your particular environment, and so on. And all this then together allows to define the adequate requirements that you need to specify to be able to do your RHA process. As an example, it's easy to write, in a requirement, we should have no component sensitive to any destructive effects. It's easy to write. How are you going to verify this? Are you going to test? Are you able to test all these parts for all these effects? So you have to put more thought about this. And then understanding the risk, you can define what you want to address. Most of the time, for us, what I like to say is no data, no RHA, no RHA in French. But what it means is that most of the assessments that we do is based on radiation testing. So here we see it's all about a balance. We can have educational mission where we may want to accept more risk. Or we can have high-class mission where we want absolutely no risk because it's extremely expensive, because we have only one opportunity to launch in many years and so on. So these concepts at very high level will then drive and flow down into the RHA mission. And that's also an important message, is this risk bucket that you take. People that say, yeah, I accept the risk. First, do you know what risk you're accepting? And then second, who takes this bucket? Is it the radiation engineer who then needs the data to analyze the risk? Or is it the project and the manager who has to? If I don't have, as a radiation engineer, the data, I can only say, sorry, I cannot make any assessment. I cannot do any magic. And then this becomes inherently a risk that the project has to take. And if this is very clearly understood and expressed in the beginning, you know the rules, then it makes life easier. So if you have any questions, raise your hand. But I wanted to start with this important point. So let's now go to the beginning, the origins of the space radiation environment, and then how it affects EEE. So we see here we have almost all the contributors around the Earth of the space radiation environment. And in fact, we have three main radiation sources. The first one are the solar energetic particles. Through the solar flares, the coronal mass ejections, they emit big movements of plasma with heavy particles ionized, like electrons, protons, and heavy ions. And these, if they are targeted towards the Earth, they have enough energy to go and reach your spacecraft and go inside and affect your components. If you are in an orbit around the Earth, well, you have to face the von Allen belts. And we are lucky, we have two radiation von Allen belts, one inner belt, mainly constituted of high energy protons, and one external belt constituted of high energy electrons. So protons, electrons. And then you have, and this for any orbit, like for the solar energetic particles, so even interplanetary, basically you will not have this, but you will have the solar energetic particles and the cosmic galactic rays, which are very high energy heavy ions and protons. Very high energy. If you are in low Earth orbit, well, you might have heard already of the South Atlantic anomaly. And right now we are here somewhere. So right above us is the main peak point of the South Atlantic anomaly. So this is actually coming from this, we cannot see, but the pointer, but it coming from the Von Allen belts and the way the magnetic belts are tilted compared to the tilt of the Earth. It makes it simplified, this part going more inside, and this is what we see here. Or here, where we see that this belt is coming inside. What it results is if you have very sensitive components, you will see a lot of errors occurring in this area on top of the North Pole and the South Pole. We will see that. And so here, if we see, for example, in LEO, and we make some a cross-section in altitude of the flux of high energy protons. So the flux is the number of particles per second. And we increase the altitude from 350 to 40, to 400, 450, 500, and so on, and so on, and so on. It kind of gives an idea of, with altitude, how this South Atlantic anomaly varies. And you see, if you start going at very higher altitudes, then you are really a lot into this anomaly up to higher altitudes. Okay, one point also that I wanted to make to you is that, so we saw this environment, but this environment is not static. It's all dynamic. And this dynamic environment is actually regulated by the solar activity. And we've heard that the solar activity has a 11, or the scientists say 22, but for us, 11 is enough, is a 11-year solar cycle. And the solar cycles and the sunspots are linked to the activity of the sun. And this impacts also the amount of cosmic galactic rays, for example, that we will receive around the Earth. So if we are, for example, in a peak solar activity here for the sun, in Leo, we will have less cosmic galactic rays, and the opposite. So basically, it's anti-correlated with the flux of cosmic galactic rays. And the same for the Von Allen belts. When you are in the peak solar cycle, you have an expansion of the electron belts and the contraction of the proton belts, and vice versa. So this dynamic part is also something that we have to take into account for very precise assessments of rates or TID measurements and so on. So the environment, we have the tree source, it's dynamic, but we have also for different environments, and different orbits, we have different environments. I will not go into the detail of all this, but this is to show to you. So here is a sort of a plot that we use to measure the dose in the first approximation with regard to the shielding. So the amount of total ionizing dose. This is for displacement damage. This is for single event effects. We will go through that. But this is just to show that the environment in GEO, for example, for cosmic galactic rays, is much more severe, it's in logarithm, much more severe than on the ISS, thankfully for the astronauts. So the environment is unique, and we have to address for each environment the radiation environment. And there are many factors that influence this environment. So the orbit trajectory, the solar cycle, the duration, the shielding, the position of the parts, how the parts are also used are all points important to understand how they affect the components. That's just a quick example because we're in the CubeSat symposium. That's an example of a rough estimation of the amount of total ionizing dose only with regard to the altitude and the inclination. And then we see here the internal Von Allen belts and the external Von Allen belts. Usually, LEO satellites, as we see here, for all the inclinations, up to less than 1,000 kilometers have not that much total ionizing dose, less than 1 kilowatt per year. But the dose depends on where you are internally in your CubeSat, because in the middle, where usually the battery is, you're more shielded from than from an external PCB. And so what do we do? Because we have all this environment, we have the requirements that we need to establish and so on. And how does this goes down to the part? So we assess at a top level all these points, and then we have to go down to each single part. And we do this first by propagating the environment. So we have tools to simulate this external environment. And then we take, for example, the example of MTG. It's the Meteosat third generation. We built some models. So here it's a model built with FastRat, where we use also the ray tracing technique, like you presented on the first day. And then we go up, down to the single part to know each part, what is the dose level that it will receive for that environment. So now we went from the environment, we propagated the environment inside the satellite to the components, and now I will try to present to you how these components are affected with this environment. So first of all, we have total ionizing dose. Schematically, we can see here that I should be careful not to fall, but here electrons and protons can generate total ionizing dose, and we see all this plus, plus, plus. These are positive charge. Actually, the main issue is on the oxide of the components. You have positive charge that accumulates. The more oxide you have, the more positive charge, the more it messes up with the electric field and so on, and then will degrade your component. So total ionizing dose is on the oxide. Displacement damage, on the other hand, due to protons and some electrons, happen in the bulk, in the silicon, where it creates some defects on the very well structure of that silicon bulk. So it basically, we can say, creates some holes and some other defects that may lead to degradation of the parameters. And the third effect that we have are single event effects. And these mainly occur also in the bulk, where they generate positive and negative charges, which are then taken in components where you have electric fields, and then may create glitches that we will discuss soon. So this is just a very basic explanation of how these particles interact in electronic components. And so we have this environment, these particles that induce these three types of effects. Displacement and total ionizing dose are called cumulative effects. So they will slowly, or not, but they will progressively degrade the part, degrade the performance until your part is out of spec, or the part is simply not functional. But it goes in time. On the contrary, single event effects are random. And that's very important even for CubeSats. Random meaning that you have the same chance of a SEU happening in the first minute your satellite is in orbit than at the end of the mission. It's the same probability. So you see already, like, if you are working on a CubeSat, which is not going to be for a long time in orbit, which do you think should be the best issue to address? Is it cumulative effects, or is it random effects? So I think maybe now you see why single event effects are much more important to be addressed than total ionizing dose. I didn't say we shouldn't address total ionizing dose, but if we have to choose, you know which one I would choose. Okay, so that's just an example here. I will put that table without entering into too much details, as you can read that. But here is just an example of what we measure. So we measure, for example, one parameter with dose accumulating, and we see how this degrades up to a certain dose. And then we perform some annealing. I will not enter into the detail to see how the response happens. Basically, ionizing radiation is much more important than total non-ionizing. And in fact, total non-ionizing is mainly a concern for optoelectronic components, so optocouplers, detectors, photodiodes, phototransistors, solar cells, and so on. Whereas total ionizing dose are for all parts, bipolar and CMOS technologies. We saw total ionizing dose, total non-ionizing dose. Now, what about single event effects? Under one umbrella, actually, you have many types of effects. I will not discuss each one. Each one has their own specific mechanism and so on. Here you have some start of explanation. But what I would like to highlight here for you is that you have two main types of effects. Ones that are soft, that the part can recover from. So like bit flips in memories or multiple cell upsets. And some that are destructive. Parts will fail. And here we have this special case of latch-ups. So a little bit comment about latch-up because we hear it also a lot addressed for CubeSats. We consider latch-ups, so what are latch-ups at the end are, in simple terms, it creates a short in your component. And suddenly you have a lot of current flowing, which can hit the component and can lead to its destruction. By default, we consider latch-ups as destructive. Now, more and more people use components even though they are latch-up sensitive. Before, we used to say latch-up, we don't use it. To be able to use for space, we would like to see a demonstration by testing that this latch-up is not destructive. Because in some cases, even if you are able to protect against a latch-up, it happens so fast that it can fry your component. So that's why we make this difference between destructive latch-ups and non-destructive latch-up. Until you haven't got test data to prove otherwise, you have to consider the latch-ups destructive. Okay. On top of that, if latch-ups occur, they may induce latent damage, which is very difficult to address. So here, a bit of an example on COTS components, which was used as a memory on ProbaV, which was targeting, which had a payload to monitor the vegetation, so V for vegetation. And this memory actually was latch-up sensitive. It was not expected. I will talk about it a bit later, but it was latch-up sensitive. And here I was monitoring a bit like where the latch-up occurred, and that's why it is useful when you have a satellite in orbit to have a timestamp. Because if you have the timestamp of when the error occurs, you know where it occurs, and it kind of gives you an idea. Is it more like this? Because then it's really a radiation, it's very likely a radiation-induced issue, or is it more random and it's due to some other electronic design? Because when there is a problem, often people say, yeah, it's probably due to radiation, but we are not sure. And sometimes the issue is not because of radiation, but just because of poor design or other issues. So we see here how the latch-up accumulates. And then we did some laser testing here to see where was the sensitive area. And actually here, it was everywhere. So if we had continued, we would have seen everywhere, basically, this whole memory was latch-up sensitive. Fortunately, it was not destructive latch-up, and there was redundancy, so we could switch to the redundant unit when it was latching. So for example, when we have an SEE, what do we do with that? When we have soft errors and SEUs or transients and so on, we want to know like how often they occur. For this, we take on one side the environment that we simulate with tools like SPENVIS. It's an ESA tool. Omer is a CNES tool from the French Space Agency and TRAD. We have the environment on one side. On the other side, we do some memory testing. So this was some memory test setup, a bit horrible, but during my PhD I did. And then we had here a cross-section. Basically, in simple terms, it kind of plots the sensitivity of that memory for that effect for different types of heavy ion LET, which we consider as ionizing energy, let's say, to be simple. So the higher we go in LET or ionizing energy, the higher the sensitivity, which is the cross-section. We combine, we mix this. It's no magic. There are lots of assumptions, and you need to understand these assumptions to be able to know what value you get. Like every software, if you enter garbage in, you get garbage out. And here, it's also very important. You have parameters that you need to know experimentally, based on knowledge and so on, to be able to do the right assumptions, to be able to get a right number. But this number that you get here is an average rate. An average rate meaning that it's not the probability that this error will happen. It's if you have this memory in this environment for a very long time, on average, you will have that rate. And that is very important to consider for high availability requirements. So here, a quick word about mitigations, because some people say, yeah, mitigations for radiation, we shield, problem solved. Well, that's not true always. In some cases, we do, and we do analysis. Here, for example, it was a ESA mission where I was working. And then for this equipment to be used, the environment was too severe. So we did some analysis with our colleagues in Airbus, and then we saw that by increasing just by 1 millimeter the thickness of the top shielding of the equipment, we were able to reduce the total ionizing dose to the levels at which this equipment was working. But we had to do this analysis. For CubeSats, we cannot really increase a lot the shielding. It's not that easy. But actually, the orbital lifetime is the driver for the total ionizing dose in LEO. For SEE, however, you cannot shield. For example, here you see like if you increase really a lot the thickness, you can see almost the opposite effect. Yeah, you have a question? So for the shielding, usually we use simple materials like aluminum. So here we just increased the thickness with aluminum, and we saw that that was enough. If you really need, then you can go into very more exotic materials. Since I've been working, we had never had the need to use that.
To understand which thickness is better for your use, do you guys do tests or analysis using something like ANSYS or?
So for total ionizing dose, we do analysis to have an idea of how much from the external environment, how much environment will go around your component. But then you always need to know, on the other hand, how much your component is sensitive to. And then you compare the two values. You say, this component is okay up to 100 kilorad, and on my environment with simulation, so 100 kilorad is with testing. And this, from the environment, you say, oh, I will receive only 50 kilorad. So 100, 50, I'm good. Okay. So now that we've seen a very brief overview, how do we do in the usual, what I call low-risk projects are the usual traditional ESA projects. So you're familiar with the usual phases. Phase A is the very early phase. Phase B is preliminary up to PDR, preliminary design review. Phase C up to CDR. Phase D is when you start to between phase C and phase D. No, in phase C, you finish the design. Phase D, you actually build it, test it, and phase E, you are in orbit. You're familiar with this V cycle. So actually, one very important point is all the RHA activities, they happen here. They don't happen here. And that's also an important message I want to tell you, is because I hear people saying, radiation equal environment equal environmental testing. We will do it later in phase D. That's not right, because it's too late. If you don't think about radiation before and you only test at the end and it fails, you have to restart from the beginning. That's why we do everything here to be sure that once it's there, after CDR, we've finished 99% of our work. So what do we do? In phase A, we have the environment definition, the RHA requirements, and we start doing preliminary studies. In case, for example, you have a very important detector that you absolutely need for your mission, we can start to do some testing there to see, is it going to be okay for the mission? Because the whole mission will be built around this. During phase C, you iterate, you finalize the environment, you start to define your design, you do the simulations, the analysis that we saw before, you start to assess whether you need more shielding or not. And then you arrive in phase C, where here, you really need to have all the test results that you need. You finalize all the work, and you finalize your design, including radiation, and we do what we call radiation control board. I will explain a little bit what is this review that we do, which is not necessarily known. And then in phase D, there are some minor stuff that I will skip. And in phase E, in case of failure, then we do the failure analysis. So a quick word I wanted to tell you about RHA requirements. And at the end, what I found when I was working is that requirements are very good. First, they need to be written properly, because otherwise they don't make sense and you cannot verify them. But most importantly, and it's the same for the ECSS requirements and so on, it's very important to know what is behind the requirement. Like what is it? What is it? Why is it coming from? Where is it coming from? Why? Because in some cases we may not be able to respect that requirement, and this is where, to be able to waive that, you need to understand what was the reason behind. So RHA requirements come from environment, the risk that I mentioned, and the mission's objectives, okay? And this then leads to, I tried to group the RHA requirements, because I don't want to go into all of them, into few groups. First, how much you allow for destructive effects or not, or you don't allow. How much margin do you want to have, mainly for total ionizing dose and total non-ionizing dose? How much error propagation or not you accept? How much availability or reliability is required for each of your system? And then some other requirements on more the methodology, the number of samples, and so on and so on. So basically, these are all the groups where you start to have the requirements. And all these points need to be addressed. So when you're addressing RHA, you need to not only cover, are my parts not going to be destroyed? Okay, that's good. But if I have requirements on availability, or if I really need this equipment to be on when it's passing, anytime I need it to be on to communicate, well, I need to be sure that when it's passing on the South Atlantic anomaly, it will stay on and it will not reset, for example. So we have the environment, we propagate it to the components, we got all the effects on the components and so on. So the question is, how do we test for each of these effects. So for each of these effects, we have different types of testing that are for space in ESA also non-negotiable. There are some new alternative ways of testing. In space, we remain conservative because we know that this way of testing are either the most representative or the worst case. For total ionizing dose, we do cobalt testing, and this has been historically shown to be the most conservative and to be the worst case for total ionizing dose. For non-ionizing dose, we do high energy protons, and for SEE, we do heavy ions and protons. So here, with this slide, I want to show you a little bit that even if we do the testing, already in the testing, there are lots of simplifications. And it's important to be aware when you do the test to be able to understand how much extra risk you're taking or not. But this is where the risk goes onto the radiation. So this bucket goes into our work, and it's our responsibility to address this risk. Because when you do the testing, you test with single energies. You test the component in normal incidence. You accelerate, so you have many particles at the same time because for a 10-year mission, you will not test it for 10 years, and so on and so on. In space, you have a continuous spectrum of energy. You have mixed particles acting at the same time, so these three effects happening at the same time. You have particles not going here like this, but going like this, from any direction, basically. And you have particle rates which are lower. And in some cases, for TID, with bipolar technology, particle with lower rates is worst case. You will have more degradation due to enhanced low dose rate effects. So we have this feeling, less rates is better. And some of the things in radiation are not intuitive. So that's why you need to have a proper understanding to understand what is acceptable as a risk or not. Here, okay, a little bit of video to make it a bit nice. And this is a facility in Belgium, in Louvain-la-Neuve, and I have my colleague and me, we were doing some testing, a heavy ion testing of band gap voltage reference, which are sensitive to transients. So here we have the particles inside this vacuum chamber, and we have it in vacuum because on the ground we cannot simulate the highest energy. Here we see actual transients happening during the irradiation, and we see the output, how it goes. And why we have all this in vacuum is because with this facility, for example, it's impossible to have the high energies that we have in space. So we need to have vacuum so that the particle can go and penetrate inside the component. So that's also a difference from in space where we have much higher energy. And so basically when we do this type of testing, it's 8 hours, 16 hours of testing, no windows during the night and things like that. So you need to like your work to do that. This is the, oops. Can you press play, please? Thank you, obrigado. So this is the cobalt facility that we have in ESTEC. So just to show you a little bit, of course, because there is also, when we do the testing, a lot. So we need to be sure about the environment after the irradiation. So here we have basically cobalt rods that are exposed when we want and will irradiate the whole room. So the rods are hidden in this mini bunker. And when we start the irradiation, they are exposed and they start to irradiate in the whole chamber. And these were the same band gap reference that we were testing. And then once you've irradiated, you go and measure the parameters at a certain TID. Then you go back, you continue the irradiation, you measure the electrical properties, and that's how you see the degradation. Okay, and why we have this table is basically to play with the dose rate. The closer you are to the chamber, the higher the dose rate. The lower, the more back you are, the lower the dose rate. And for bipolar technologies, it's better to go on the back. So these are the things that we specify in requirements, for example. So what do we do every day? Actually, it depends. It depends on the company. It depends where you are in the customer chain, we say. But we are usually involved in all the disciplines, and we need to be aware of how is the environment defined? How are the models? Are they conservative or not? What are the parts? In general, which part is sensitive to which effect? How do we do the testing for this part? Do we know that for this new part, maybe having tilting is more of an issue than normal incidents? And so on and so on. So we do a lot on every aspects. And for these main, so low-risk missions, we have two important things: radiation analysis and radiation control board, which are the two reviews I mentioned before that I will just briefly explain to you, in particular, like why we do them. Because it's, of course, it looks like, paperwork, ECSS, but there is a reason for that. The radiation analysis report is actually the report where you see the project from the radiation point of view. But you see it from the beginning, like from what are the requirements, what are the components that we agreed that they are sensitive to which effect, and how do we have the test data for each of the parts? How were they tested? Is it in the same application condition? Do we have the number of samples that we have agreed? If we see that parts have an effect, how do they propagate? Is it critical for the system or not? So basically, it's a very methodical work that is reviewed by the radiation engineer. And you go from all these things that I mentioned, the RDMs, the effects, propagation, calculation of availability. And basically what you're doing, you have all the top requirements. You go to the bottom of the components, and then from the components, and you know what are the effects, you go back on the top to see what is the impact at system level. And this whole process is very important. This is where we do this main radiation control board, and that's the other one. And I will explain in the next slide this review. But let's say that this RCB is sort of a CDR for radiation engineers. But we need to do it before because we need to freeze some things on the design due to radiation before we go to CDR. And obviously, all the testing must be done before because then we have all the data that we analyze in the RCB, for which the main document is the radiation analysis that I showed to you before. So here, what happened in the radiation control board? So in simple terms, as I said, it's like the CDR for the radiation engineer. So we have many inputs: the component list, DCL, declared component list, the design. It's important to know the design, the radiation analysis report that I mentioned, all the test reports, lots of other documents, the failure mode and effect analysis, worst case analysis, part stress analysis, and the environment, the shielding, and some other works. And all this is done, and you can read this later, but to make all these assessments from how do we test to sensitive, each part sensitive to different effects. And I have this beautiful memory where suddenly I have an SEU. Oh, okay, SEU is not destructive. But imagine this SEU is the register to say that my thruster should be on or off. And then this SEU propagates, this error propagates in the microcontroller, goes to the interface, and say, switch on the thruster. Then you can have a wrong orbit. You can go into a wrong orbit. So it's just a silly example, but to show that if it's not designed properly, a simple SEU can lead to a big consequence on your project and put it at risk. So that's why understanding how each component responds to various radiation-induced effects is important to understand how they. It is important to understand how they propagate and their impact at system level. And that's why radiation is not only a work done at component, but it's looking at the system overall. So that's why I said in the beginning it's linked to engineering also and the design. And we go and look at the design. The design, do we need to, if we have here transients, do we need to filter to avoid that the transient propagates and so on and so on? Because why? Why? You say, okay, but I am using a radar part, radiation hardened part. Imagine you're super rich for your CubeSat mission and you're using radiation hardened. So you say, okay, there's no problem for radiation. Hey, but look at this data sheet. It's radiation hardened against latch-ups, but not against transients. And transients can happen. And if they happen, they can create a glitch to switch on your thruster. They can create high voltages that can create a voltage spike on that component here, which cannot tolerate that and will break that component. So that's why propagation is very important. And that's why even for radiation hardened component, we look at these effects. Another also concept to go a little bit more into the details, but that people ask is, and these are then also requirements on how many samples or how we do the testing is, why do we test so many samples? Because there is lot-to-lot variability and part-to-part variability. What I mean is, for example, let's pretend we have the same lot. So they are all brother or sister components from built exactly the same. Each one will degrade differently. This one degrades much more than that one. Or here, even if we don't have, and it's coming from different lots, we can have even bigger difference. So let's see this one, this part, it was the same lot. So all the components were brothers, and these two were degrading much sooner than this overall system. That's why we need a lot of samples, because if we had only tested one which was inside, we would not have known about that one. So what we use is we try to have as many samples as we can, and then we do some statistical analysis to predict what would be the range of degradation. And then we use the worst case degradation on the statistical analysis to say, okay, this part will very likely survive up to that level for this total ionizing dose. Not this, not this, that level. And then we see, is it okay for the environment that I have? Okay, I will speed up, I think. So basically, here I introduced like how we do for the usual ESA projects. Try to not enter into too much details. The risk mission. What? For example, I worked on the SMILE mission, which is a science mission in collaboration with the Chinese Space Agency, where ESA was providing the experiment. For example, another example of here a CubeSat. I'm working on Enon, which is a 12-unit CubeSat that is supposed to go on the L1, L2 orbit to analyze the solar flares and to be able to warn the Earth of a solar flare that is going to arrive. So as part of the space weather awareness program and so on. So these are two different examples. One is a medium risk, one is a much more higher risk. And so basically, there is this continuous trend, about this new space, so on and so on. And it's one word to define many things, this new space. But we have actually not larger cost, but I meant larger cost constraint and time constraint, and the willingness to use more and more powerful components that are not radar, that are not built for space, and that we need to address the risk here. But the problem is, people come and say, yeah, new space, we do it like, we do it, we know how to do, we will do it. So, but traditional space, new space, they are all exposed to the same radiation environment at the end. So we need to tackle this issue. It's not because new space that you have new radiation that will not hide, and you need to consider that. And so basically, how do you do? Because if you have constraint in terms of budget, for example, for your CubeSat mission, you cannot have everything for everything. You have to trade. If you don't have money, if you don't have time, you trade it with more risk. And that just needs to be accepted and clearly agreed. And once that is agreed, everything goes back, because then you know, okay, I don't have money, I don't have time, I will address the risk, and I will take the risk on this, but not on this, for example. And then on that part, where you don't accept the risk, you do the work as properly as possible, and on the rest, you accept to take it. So that's a decision that comes really at the project level. An example, so here, a non-CubeSat example, I thought it was interesting to show a bit something different. So on SMILE, it was a bit new. It's supposed to embark a X-band transmitter, and I had to work on that because due to regulation constraints and so on, we could only use a fully COTS-based X-band transponder that was already flown in LEO, but not on this very highly elliptical orbit of 5,000 kilometers and 140,000 kilometers altitude elliptical orbit that is crossing the von Allen belts, that is generating more total ionizing dose and so on. So how did we do that? So it had a heritage. It's a good start, but it's not everything heritage. It was not built for a HEO orbit. And here we could not do the traditional approach. So we had to find a trade-off. Okay, that, forget about that. So we defined first, like, what do we want to do? We discussed with the managers, like, what do we want to achieve? Because I cannot do miracles. So we want to reduce as much as possible the risk. Okay. And we accept that we cannot have all the requirements initially set. Basically, we are accepting more risk. Okay. So that's the thing. Then we start to discuss, how is the configuration? And that's how the part is also linked to design. Okay, there is redundancy. That's a good point. It doesn't do everything, but it's a good point. We switch it on only for a small amount of time. So it reduces the risk that when the this equipment is on, it's sensitive to single event effects. Plus, bonus, it was already protected by LACW with some data there. Okay, so we have something to work with. Is it enough for us? No. Because we had defined what was good enough for us. Said, we have this, now we continue. So what did we do? Iterations between the industry and us to what critical parts to select, lot procurement. And why is lot procurement important? Is because what I mentioned about the lot-to-lot variability and part-to-part. If you don't have the components from the same lot and you have another lot, you need to redo the testing. Otherwise, I cannot guarantee as a radiation engineer what's going to be the behavior of this new lot. So we used where we could some previous data, and we consolidated the approach. And that's why, remember in the beginning, I said, oh, we increased the thickness. So thanks to increasing the thickness, we handled TID. And then there were still some components for SEE that were critical, that were not tested for this environment. The power MOSFET, the RF amplifier, and the potentiometer, because it had some digital stuff inside. And we knew that these were potentially sensitive to destructive effects, and we had to test them. And we tested also some other parts, like the microcontroller, the CPLD, sort of a simple FPGA, the pulse width modulator, optocoupler, and so on, so on. And we did the radiation analysis to analyze all the transients and so on, to check that the availability was met in a radiation analysis report. So I hope it starts to make sense, because all this is, at the end, the same thing. Okay. Now, this is an important message. So we saw that we had this COTS equipment. It had heritage. Does it mean that I can just reuse it because of this magic word heritage? No. Also, because of the inherent issues of COTS, so there are two concepts here. First, when you buy a COTS, it's cheap, but you very rarely have the traceability. The traceability to know that what you test is going to be the sensitivity of the part is going to be the same as the one that you will put in your satellite. If you don't have this traceability, you have no guarantee, you have more risk that what you're putting in your satellite is different. Are you willing to accept that risk or not? That is an open question that needs to be clarified in the beginning of a project. But if not, then you need to buy the same lot and test it. If it's not working, you have to throw the lot, buy another lot. Because once you have a lot and you have a part that works, you can use this lot with higher confidence. And I say higher confidence, but it's not the same concept for COTS lot as the space radar lot concept, but I will not enter into the detail. But basically, because of lot issues, because of unknown radiation data, if you need to have something to fly in space, you can buy it cheap, but then you will need to pay for the testing afterwards. You will need to pay to buy the lot. You will need to pay. So based on the risk you're accepting, you have to keep in mind that there is a hidden cost of COTS. And this has to be considered from the beginning, not to fall into issues. So I was mentioning traceability. I will come back to heritage a little bit later. Traceability. Look at this part. This is the Proba one. I showed the example before. We bought exactly the same reference, same package, same performance, was well tested and so on. Great. But we tested it. It was not sensitive to latch up. Why did it start to latch? And then there was an investigation that was done. The part that was tested was this one. This one had this sensitivity, so the cross-section for different heavy ion LET. So it was good enough for Proba. But actually the one that flew, that was bought to be put on the satellite, was this one. You see the difference in the die? Whereas if you didn't open, it was the same component, same performance. And that one was much more sensitive. So this is what I mean by traceability. When you buy COTS, you don't know what's inside. You cannot guarantee what's inside. And to guarantee it, you have to pay for it. And that's one information that you pay for when you have radar components, because you have this traceability to where it was manufactured, from which wafer it's coming from, because that's important in radiation. Here, you don't pay for that, you don't get, and this is the issue that you can get. Thankfully, we had a redundant system to mitigate, and the latch-up was not destructive.
But this is not a problem for radiation, it's a problem for product assurance.
Yeah.
Product assurance failed. Not, it means if you made the test, and the test was good, you could use this component well.
So,
but if during the development of the project, people changed the components, not a graduation process, it's a product assurance process.
So the component was not changed. This component and this component had outside the same reference, the same markings. It's like K6R4 TC10, K6R4 TC10, ta 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 ta. The only thing that changed was the date code, because they bought it at different time. But it was the same component.
That's not.
And exactly, it's not.
No, that's not.
But for you, it's obvious. That is great.
If they have a different time, a different batch, they are other components.
Exactly, and I'm happy you agree with me. But a lot of people are not aware about that. So when you test COTS components, You have also other issues now, more and more, because you have very performant components. In some cases, we cannot even test it with the means we have on ground. When you have flip chip components, you need to do more work to be able to make sure that you can test it because of the energy of the particle and the penetration. I don't go into the details, but it makes it complex. More and more, some parts that we get, we say, sorry, we cannot even test it. So the earlier you know, and the earlier you can change these parts to be able to have those that you test. And this is becoming more and more challenging. And why? Because to be able to test, if you have a component which has like a dissipation plate on top and the bottom of hundreds of micron, that's enough for particles coming from here not being able to go inside. And if you don't know, you test and you say, ah, good, it's not breaking. But actually, it's just because the particle is not going inside to the sensitive area. Another misconception on in the new space world, or people who don't know, is this: is protons vs heavy ion. And there's often the question, because when you do proton testing, you don't need to open the component because the particle will go through, even the package and so on will go at high energy. For heavy ions, you need to open to be able to start here and then go just up to here. So instead of doing all this work, we do proton, it's easier. So I want to show you an example here to illustrate what I will say later. Is here we tested with 10 to the power 10 protons per centimeter square, and we saw, so not me, it's coming from here, they saw 3 errors, 3 areas where there were errors, for 10 to the power 10. Now, let's pretend we do the test 1,000 times with 1,000 times less particles. So 10 to the power 7. So we would expect to have less. This is what we get as errors. Basically, this is to say to you, try to illustrate that it's also about risk. All the errors that we could see with heavy ions, we saw them with protons. But sorry, the opposite. All the errors we could see with protons, we could see them with heavy ion. But all the errors that we could see with heavy ion, we could not see them with protons. Heavy ions are able to detect, able to show you all the types of effects that the component can be sensitive to. Proton will not give you the whole picture. It will give you only a partial picture. Are you willing to accept the risk? It is an answer to be answered depending on the project and the risk you're wanting to take. But that's why for traditional space, we go for heavy ion, even if it's more complicated. So here I will go a little bit faster because I think I am. How am I doing with time?
It's okay.
It's okay. Quickly about board testing. I want to say, because people think, we will test with the board in proton. So we know proton will not reveal all the effects. But the good thing with protons, we can irradiate a full board at one time. So people say, let's do protons. But it's not, there is also some risk at program level to be considered, because to have a board ready, you usually are close to the CDR, or normally you've passed CDR. If after the testing here, something fails, you have to go back to the redesign and will create issue. So you have that if it fails, you may need to change the design. If you're testing with the board during the testing, if failure happens, you will not necessarily easily know which part failed, and so on, so on. So you have to think about how to test it to be able to see which are the sensitive parts to be able to know. So it complexifies also the thing. And you may need to retest if you're redesigning something, you need to retest the board. You may need to test several boards because we need several samples. So it will cost also more. You need to have the board ready before CDR to be able to do that, and so on, so on, so on. So there's a pro and cons. There is no right answer, but you need to be aware of this to be able to take the right decision for your project. Just as an example here, coming from a colleague, I cannot say which mission, but there were 2 boards tested with the same code part. One failed below 10 kilorad, one passed at 16 kilorad. People say like, it's the same, it's the same, it's the same. It was indeed the same voltage. It was not the same current condition. When you have the solution, it sounds obvious. When you're testing at a whole board with many parts, with many things, it doesn't. And here, the issue could be attributed to lot or to the application. We don't know. We will not have the answer. I will also not go into all the details, but you can read here. The message that I want to say is that people say, okay, bon, I will just mitigate and then the problem is solved. But if you throw mitigation, basically, so here the message is like blindly throwing mitigation here and there doesn't guarantee a better system. What I mean by this is like, okay, I will protect with many latch-up protections everywhere. Yeah, but if you just throw latch-up protection everywhere, you're adding more components, you're adding more risk that because of the design, something fails and so on. If you're protecting against latch-up, but the system you're using is not radiation hardened, you're creating more risk, because if this has an issue, it will impact your whole design and so on. So you have to think about which mitigation and where you need, and specifically only where you need. And ideally, you know it only when you have done testing. And what matters is to have the right mitigation only when needed and understand the impact at system level, where you are not mitigating, to be sure that it's not impacting your overall mission. So this is a bit of a repetition, but we have the same environment. There is no miracle solution. Sometimes people, they give me the DCL and they say, can you say if it's okay? Okay, if I don't have the radiation data, I can look at parts, I will not know. How are they used? How is the design? So we need to have data. Codes are not cheap in reality if we consider that we need to do some radiation testing, and on top, no data, no RHA. Be careful about heritage and off-the-shelf equipment. Okay, so that here I wanted to come back with heritage, because people say, yeah, I have heritage. But heritage for us to be valid is, is it the same environment or worse? Is it the same electrical condition? Is it the same part from the same lot? Is it, and so on and so on. So all this information is very rarely available, and you can have something that flew that was not an error, but remember that SE are random effects. You can have the same component in the same platform on the same orbit, and suddenly you are bad luck, and here you have the part that fails. That's why we do testing, because when we do testing, we try to put even more particles than we have in the mission, because we want this part to tell us all the mitigation, all the types of effects, and make sure that there is not a case where it may be sensitive to destructive effects, if I simplify. And so the most important is to have a balanced approach to radiation, to have the full system in mind, and to understand the risk and where you are taking the risk. Let's say you say, I want my platform to be tolerant to some effects at least, and so on, so on. But the payload, I have no money, I don't care, whatever. If you say that, okay, it's a project decision, but at least you have to be careful that there is no error propagating from the payload to the main platform. And that's what we called the safety barrier. You need to be sure that even when you are not handling that the interface components will not create an issue. If suddenly you have a communication component that you use for communication that breaks and is throwing constant garbage on the communication bus, you may saturate your bus, and it may be an issue that we would say propagates. So the main message is start the considerations early. Doesn't mean start the testing and so on, but think about what risk, what environment, what requirements, what do we need to do, and then you decide what parts you need to select, want to reduce the risk. And that's where we do this. And the main essence is that we iterate a lot in the beginning to avoid issues after. And we focus and we define with the project, like, what are the critical functions? What are the critical components? And then we focus the work on what we think is the most critical for the mission and what is the most critical in terms of radiation. And this leads me to the introduction of the ESA mission classification. This is some blah blah of why we do that. But basically, you know now, is because we have to handle the risk in a different way, from the traditional ESA missions to the educational missions. So here I'm showing something that is ongoing work. So we are still finalizing all this, but it's just to show you that this risk concept in radiation, we've tried to dilute it into the way these requirements are tailored. So if we go here, low risk mission, fully CSS applicable. And then here we start to degrade what is applicable, what is less applicable. And then we go, for example, for CubeSats, usually they are more into these two. That's the most realistic in terms of risk and overall budget. That's more like deep space CubeSats. That's more like in-orbit demonstration CubeSats. Here we do heavy ion testing on critical parts and proton board testing for SEE. Here we do, if you want, proton board testing on what the project says is critical. If they say nothing is critical, then we don't do. So we tailor it on what is critical. And that's the important word. And that's a discussion together with the project. You see, for example, I mentioned total ionizing dose is a concern. For Class D, we don't even care about doing TID. We say, okay, we take that risk. But SE, we need to do something. We need to have mitigations. And we need to make sure that very sensitive parts are not selected. That I will not read. This is just to tell you that in radiation, the devil is in the detail. That you have to go into the very detail to say, like, in the requirements, like how many boards, how many this, why, what risk, what not. And then only you understand if this approach is good enough for you and if you can afford it or not for your mission. With this, I finish the radiation brief overview. And now I wanted to just take the opportunity of being here to present some of the in-orbit demonstration CubeSat missions and technology that we are developing in ESA and in TEC, which is my directorate. And TEC SPC is the directorate led by Roger Walker, who is leading all the in-orbit demonstration CubeSats activity in ESA. But there are also other CubeSats activities in other directorates. So you see, we started with the CubeSats for the Vega maiden flight in 2012. I was fortunate to be part of that. It was really nice. It was educational. And then slowly, in time, the complexity of the missions we've been working on in ESA has increased in all the areas, basically. And we are here in the launch to 2016 on Henon, a deep space CubeSat mission, which becomes more complex because it needs to handle radiation, because its objective is to be able to work when you see a solar flare. So that's a nice overview of all these activities. So you have some that studied the re-entry, monitored climate variables in SIMBA, just technology demonstration. Then you go and you have, for example, Pretty on demonstrating GNSS reflectometry, which was also discussed this morning. A smaller version of the ProbaV. Sunstorm, which was measuring X-ray fluxes. We discussed about that this morning. This one, SROC, is going to be going around sort of a plane, like a, yeah, I forgot the name, but it's like Dream Chaser, but it's being built in Europe. And this one is going to do some inspection of that. Then we have some formation flying satellites, and so on and so on. And here we have all the developments related to deep space CubeSats. And recently we had the launch of Juventus in Milani, where I worked a little bit, which is hosted on board ERA, going on this DD Moon and DD Moss asteroid to study the impact of the NASA DART mission on this system. And here we have some other things more on the Earth observation side to detect wildfires, to do some visible imaging of the Earth, and here to monitor some stuff related to agriculture and soil temperature monitoring. But we do satellites, and we not only do that, but we try, or their section, try to develop also the key systems that are then used in those. Because once you have these building blocks, then you can develop further and further. So for example, for the deep space missions, it's important to have an X-band transponder, so to be reused on several deep space missions, and so on. So you have deployable antennas, thrusters, etc. And with that, I conclude the presentation. So radiation effects on electronic have a direct impact on reliability and availability of a system, and therefore on the success of the mission. Radiation hardness assurance, now you know what it means. It should start even for CubeSat mission at the early phase of your design, ideally, to start considering what you will need to do or what you need to address. And it's all about managing the risk. We cannot avoid it for sure. It's all about reducing the risk as much as possible for the mission to be successful. We discussed quickly about the tailoring and how we go towards the most critical parts on the higher risk missions. And then this importance of having this top-down, down-up approach balanced to be able to do as much as you can within the constraints and the budget that you have. And of course, we didn't introduce all the things and didn't go into the details, but I hope that this was a good introduction. It was simple enough for you to keep in mind some of the main messages I wanted to transfer to you. And with that, obrigado for your attention. And sorry for the delay. And here I've put all the standards and so on. That's always useful to go and have a look at if you're interested.
Thank you, Luis. It was a very interesting and instructive presentation for the students. I think they are very motivated even more with the radiation problems that we face in our designs. And we still have time for questions. I think Lois.
I was in a NASA workshop in Langley, and I was very interested about secondary radiation. Yeah, that means you put a shield, and the shield acts against you.
Yeah.
So what you wanted to protect, at the end effect, it's causing more trouble than protecting. Yeah? And they gave me an example of the James Webb Telescope that they have this problem there from secondary radiation. Can you talk a little bit about that? We perhaps have some guidelines to try to avoid the secondary radiation?
So secondary radiation becomes an issue actually that is not extremely common. When you have it becomes an issue either when you have very thick shielding or you're using exotic materials which have very high atomic number, high Z material.
Like copper.
Like copper and so on. But when you have like very thick copper and so on, then it becomes an issue. And then at the time when I was trying to understand why I trying to make myself a mental image, like why? Because if you increase, the shielding, why would it be worse? Because if you do it not right and you don't design it right, actually the particle will go, but will transfer its energy to many more particles that will not have as high energy as the initial one, but it will sort of dilute it. But these diluted particles, which we call a shower, will have less energy, but still can be harmful. I'm trying to simplify because less energy means higher reality. But so you have, if you have very thick shielding or high Z material and so on, then you start to look into that. For CubeSats, it's not an issue because the shielding is not a big concern. We have aluminium, and in reality, in fact, when you look at components inside, you can have high Z material in the components, and they create also secondaries that can be harmful. So that's why in some cases, when you're testing with heavy iron, you think, okay, it will not be sensitive to protons. And then when you test with protons, you have a surprise because the protons interacts with the high Z material, which creates higher reality particles that goes into the sensitive volume. So for components, it's inherently embedded into when you are doing the testing. So you get this answer. For big shielding, it's not a big concern unless you have high exotic materials or very thick shielding, which you rarely have.
Any other questions?
This presentation will be available to you.
Yeah, can we share your presentation?
Yeah, you all guys have been so nice then. Yeah, okay. Yeah, the videos, no, but the presentation, no problem. Well, I'll make it available in PDF.
So I just wanted to know that you mentioned the both tests, the high ion test and the other one, I just forgot the name, sorry.
Heavy ion and proton.
In the proton, yeah. One is better than the other or depends the occasion? So you mentioned right now that the proton test could be used, in this case, could be more reliable than the other one?
Yeah, but that's a very, very specific because the gentleman, he addressed a very specific problem. In general, heavy ion is the worst, will give you the worst response, will allow you to know all the failures that can happen in a component.
Oh.
Protons will give you only a partial picture. So that's from the radiation side. And everything depends on how much risk you are accepting to take. Is this partial picture good enough or not? For example, for power MOSFETs, they are sensitive to destructive effects. They may not be sensitive at all to proton, but to heavy ion, they will completely get destroyed.
Thank you.
Yeah.
Any other question? No. So let's.
Okay. Thank you very much for your attention.
We are late, so we are shifting the session 3 to after the coffee break. And we have a coffee break that starting just now, and then we meet here again in 15 minutes. Yeah.
How long did I take?
We're closing for a
Too
coffee
long?
break.
No,
We're
no.
back in 15 minutes.
Because it was like 4:30, so I took like 1 hour and 20.
Obrigado.
Guys, I am Professor Loris from ITA. As everyone thinks that we will try to keep the time because we are very late already. And we have here Mr. Felipe Almeida. He will talk about ground station service. Please, Felipe.
Thank you. O controle para passar. Posso usar o do púlpito ali?
Pode sim.
Obrigado. Good afternoon. Good afternoon, everybody. I'm Felipe Almeida from CREA Space System. I'm here to present you the ADA and dataset, a studio noise mitigation system. This presentation, I will walk you through innovations in ground station and their relevance to CubeSat and the technical solutions we've implemented to address a global challenges in signal reception. Okay. We are seeing a growing participation of developing countries in space activities with a strong tendency toward small satellites or CubeSats. These offer affordable, flexible, and cost-effective platforms for scientific research and commercial applications. The Satellite Industry Association provided this data showing that CubeSats are driving innovation across multiple sectors. Their low cost, ease of deployment, and broader access to space are opening new opportunities for countries, universities, and even startups. Okay, so the problem. What's the problem that we've seen so far? The lack of consistent standard measurements in signal quality and intensity. Without standardized equipment and methods, it's harder to compare data across different ground stations and locations. The solution that CREA Space System is trying to achieve here is the dataset network. The dataset network is a network of antennas, standardized antennas that we were building in our own facilities. So we have the equal antennas deployed here in Brazil, United States, Africa, and so on. What's the idea? The idea is that with equal antennas targeting the same satellite, we can measure the difference of the signal perceived by each antenna in different regions of the globe. So we have the same antenna tracking the same satellite. So we know the difference of the signal received, intensity and quality, and we can map this difference across the globe. With that, we can build a database with that information and be able to reproduce or create better antennas in the future. So the dataset network is created by ADAs, what we call. ADA is an automatically driven antenna. So we have one exposed here for you to see. The solution is to create standardized antennas or ground stations to be able to capture the signal of the satellites. The ADA is automatically, and so it tracks any satellite. So with the TLE, we can calculate and put it in the system, and we can track any satellites. Okay, that's the idea. Here we have some mechanical elements inside the antenna. We have the motors, the drivers, and the encoders that we use to achieve this. Here we have an operation diagram. Here we can see the flow of the data from the satellite through the ADA and the processing signal. What is the ADA? What we are aiming for the ADA? What it's good for? It's good for commissioning, tracking, RF signal reception, remote sensing, and data processing. The processing of the data occur inside the ADA, inside the ADA. So the antenna is self-sufficient. That's the idea. Here we have some software and controls. all the operations between the hardware and the software, it's made by what we call ADA server. So it's a software inside the antenna, inside that big box, that does every calculations for satellite tracking and also the reception of the signals. Here we have some data, some information that we acquired targeting NOAA satellites, which are open, so we can produce these images. So what is the study about? We've made a study about filters. So we put together two identical antennas in the same ADA. So one has a filter and the other does not. So I will talk more about this in the future, but just for you to know, the SAW filters is what the filters that we chose for their cost effective. Here is another type of filters that we tried, helical, cavity, and interdigital filters. So we go with the SAW filters that work better for us. The results. So the results. Here we have a detailed information about the difference received in each antenna, and the antenna with the filter and the antenna without the filter. I will just pass this because we are ahead of time. Here we have the difference in signal acquisition. And here we have an optical overview with the filter and without the filter. Here we have the signal to noise ratio with the filter. This is the line that is important. The last line is the one that is important. And without the filter. So we can perceive that the filter does its job. Okay, that's not what we aim here. So what is the aim of this study? The aim was, we do this study with the filter and without the filter just to prove that we are capable of doing identical antennas. So the results show that the filters, obviously, it does its job. But the difference between the reception with the antenna without the filter and the antenna with the filter is exactly what we expected by the filter. So this proves that we are able to construct, to build identical antennas. So the idea here is just to make this study, to prove, and that we can create the data set network that we proposed in the beginning, create an array of equally constructed identical antennas all around the globe, so we can achieve our goal, that is to perceive the signal differences in different locations. That's the idea here, okay? So this is a more detailed, technically, just about what I said. Here is some company overview, our factory, our antennas. We have nowadays 5 antennas working in our facilities. We brought one here for all of you to see how it works. We have the detailed data there. We have the signal reception and so on. In our website, we have the signal that we receive from satellites. We have the audio, the image, and so on. So our focus here is to create these ground station antennas and make it a network, because we are focusing on set cubes. Everybody's talking about set cubes and etc. And it seems to us that some people are forgetting about the ground station, how to communicate to the set cubes. So this is our goal here, to create this array, this network of antennas that will be able to communicate to all satellites. And achieving this, we will have more time in connection to each satellites. Okay, that's the idea here. Here is some awards that we received already in other projects, not only this aerospatial projects. Our company has over 30 years and do a lot of things. And here is our connection. Sergio Suarez is the CEO of the group. He will be here tomorrow talking about a little more about this. Okay, that's it. Thank you.
Thank you for the presentation. Any question?
Achei que essa pergunta ia ficar para depois.
So is it the system already working?
Yes, the system is already working. The system that we brought here is reception only, but the transmission is already installed and it will be working by the end of the year.
So you guys already collect data from many satellites at the same time, and do you store that data?
Yes, we store the data in our own data center. We have multiple servers there. All the data that we collect is from open satellites, okay? So like the NOAA. And it's available on our website. You can enter there, see the images, listen to the satellite beacon and etc. It's all available there.
For free?
For free.
Nice. Congratulations for everyone that's working.
Thank you.
I had a question. Normally, when you do to install an antenna like this, we make a site survey. In this site survey, we identify possible noise in different electromagnetic frequencies.
Yeah.
It's not a better option to avoid regions that we don't have, that we have this a lot of electromagnetic, because I understand that you are using filters to
Mitigate noise.
yeah, exactly. So what do you think about that?
Yeah, I believe that it's the correct approach, but the idea here is to create the network around the globe so we can have a signal receiving from the satellite all the time. So we can't always avoid bad locations. So one of the intentions of the product is just like this, to perceive the difference of the signal received in each location. And with that data, we can construct algorithm or something like that to better create new antennas in the future.
Yeah, but if the interference is in the frequency that you are aiming to use, you cannot do anything. You cannot filter that.
Yeah, it's true. It's true.
Any other question?
No.
Thank you very much.
Thank you.
Next one. The next one is Rafael Ferreira de Mello. He will be talking about proposal and review of a ground sensor terminal.
Eu prefiro solto o microfone.
Tá legal, solto.
Como abrir esse aqui? Assim? Obrigado. Tá. Não, tá esse. Aqui. Aqui. Tem um passador. Greetings everyone. My name is Rafael. I am a researcher here at Senaisima Tech, currently working on the Competence Center of Nanosatellites. And today, I want to share with you our mission, our first nanosatellite mission, and a little bit of our ground segment GST, or as we call it, ground sensoring terminal. So we have been notified the proposal and review of a ground sensor terminal. It's going to be a lot more conceptual here. And I'm going through the mission and through some key concepts to introduce to you the project that we have been developing in the past 6 months or something. So as I've said, the objective here today is to develop the concept the conceptual overview of the project and the design for the Simatelish 1 mission. So, presenting to you the Simatelish mission, I think it's the first time it is talked about in a congress or a presentation like this. So, it is a very simple 1U mission, which has two main objectives. I brought here the image, which is the concept of operation. And our objectives are to validate a LoRa payload as a communication link, a communication radio, I'm sorry, and to have the inspection. We have these two ground segments here. One is our main ground station, and the other is the Simatelish GST. The GST will be collecting environmental data from crop fields. We have a partnership with another campus here from Senai Cimatec called Cimatec Sertão. And they are developing various researchers around quality of crop fields, development and technologies for the Sertão or the northeastern backlands. And we want to help them by collecting data and sending it back to our main place, which is here, Senai Cimatec, through the satellite. Here we have all the stages from launch to the decay, but our main focus today is going to be this guy, the Simatelish DST. So I went through the objectives, and the GST, a keynote here, is that it will serve both as a real-time monitoring tool for the crop field that it will be collecting data from, but also as a validation tool. So we can, for example, the folks at Cimatec Sertão are developing some technology to try and improve, for example, the growth of soybeans in that general area. We can use this to validate, for example, if the ground humidity has went up with the application of that technology or something like that. So our methodology, we did a really extensive literature review based on other projects, various case studies, and a lot of research in that area, not only for GSTs only, but also for weather stations as a whole. And we aim with that with this literature review to provide a solid ground for the project, and also to help support some key component that we will have on our system. For example, we want to take a look at what antennas these other projects have used, and from that, have a general idea of the main concepts that we need for the antenna selection of our own project. So, talking about the conceptual development now, we have a few requirements. Some are from our project, others are from Cimatec Sertão, but our main things are to collect the environmental data, to do the pre-processing of the data, so we can send the data packets to the CubeSat already prepared. We have to do the data transmission through LoRa, which is the second mission of the CubeSat, of Simatelish, and also have a self-sustaining power generation system. Despite being used in a campus where we have access to electricity and internet, the whole project is being developed to aim to be installed in regions that don't have that. So we're talking about scalability. If this project works, we can use it outside of Cimatec and help, for example, farmers that don't have a really good infrastructure and want to, let's say, inspect their ground or something like that. This is more of a future thing than an now application. Right here, I have a little diagram comprised of the general system that we came up. We have the sensors. Right now, I think we are sensoring 6 different variables, and we are using various communication protocols here. Just analog RS485 and UART, to name a few, and they will be sending to a microcontroller unity. This guy is the heart of the operation. He will be collecting the data, pre-processing the packets, and sending them to the radio to the lower transceiver, as I called here, so we can send to the space segment. Also, most microcontrollers have an RTC, a real-time clock embedded to it, but I decided to put there just to register. Okay, what time the communication link happened? At what time we collected data from some sensor and something like that. Also here, from the microcontroller unit, we have an SD card, which is more of a reliability thing. Let's say that the satellite did not properly communicate for some reason. The data corrupted or something like that. This SD card is here for reliability, so we can gather the data some other way in the case that the communication link failed for some reason. Also, since GSTs have a much longer lifespan, let's call it that, than a CubeSat, which is around 6 months to 2 years, something like that. The SD card is kind of a placeholder for another ways that we can store memory, so the researchers can access it. The local display interface is more of a project requirement for Cimatec Sertão, because some researchers want to have real-time access to the data being collected. So it will be a little display on the GST that will just show, for example, the temperature, the ground humidity, the wind speed, and also the time that the last communication link between the GST and the satellite happened. So here's a little bit of a application problem, because when we are talking about crop fields, plantations, you call it, there is a little bit of a problem with the data accuracy, because a few of these variables, ground humidity, even temperature, sometimes can vary a lot from one crop field to another, and this happens to cause a really bad data accuracy. Because, for example, if we had only one GST, it would be the data for all the region. So with that in mind, we are proposing a little bit of a network. So the one that we are currently developing is the master, as we called it here, and we would have a lot of support GSTs that, for example, will collect data from different crop fields. Let's say this one is a soybean, this one is a cornfield, and the list goes on. This is a little bit of an exaggeration. The project currently is only here on the master GST, but we plan to expand it if needed. This also reflects on a little requirement that we need to lower the project cost so we can be able to afford all of this infrastructure at some time. And also a little interesting fact that thankfully, as we are using LoRa as our communication protocol, we can measure how many support GSTs we can have. So during one communication link, we can send all the data packets at once. The way it works is like LoRa is a spread spectrum. I think I got, yeah. LoRa is a spread spectrum, low power, long range communication protocol. And thanks to its properties, such as the spreading factor, the coding rate, we can establish with the frequency we have and the bandwidth we have, the data rate of the communication link. So with that, we can have a little bit of an idea of how many packets we can send and how many support GSTs we can actually install. So during just one communication link, we can send all the data at once. And as a future projection for you guys, this presentation was made, I mean, this study was made during the conceptual development. We are currently wrapping up it and going to the prototyping phase. We are currently acquiring material so we can start building and actually prototyping the ground station, the GST, and hopefully in the future we can go to the communication tests and validation and the actual mission application. And at some point after this, we can talk about the scalability of the project. So the support GSTs, this utility to other people, not only CIMATEC, and the list goes on. So this is the little debrief that I chose to bring to you today. And feel free to ask any questions. And if you have suggestions, please feel free. Thank you.
Hello, I have to say to you, briefly, you are a very talented young man, and I think that you speak English very well. Did you live abroad?
Hmm?
Did you live abroad? No.
No.
So, is there any question for me?
Tem que ser esse microfone.
I have a suggestion. I don't know if you know the projects SCD in INPE, the National Institute for Space Research. They have exactly a system like this where they build what they call PCD, platform of collection of data, but they don't transmit with LoRa. And I'm sure they will like to talk to you to discuss what the possibilities. Also, Aldebaran from UF, the Federal University of Maranhão, they are here. They are doing a project like this for fish boats where they transmit the data. So there are some opportunities for you to, also in the Northeast Regional Center of INPE and Rio Grande do Norte Federal Institute, they develop a PCD also, but none of them transmit with LoRa. But I'm sure they can help you, and you would like to discuss it. I can give you some directions if you want later.
Thank you. Actually, one of the main references that we used is the PCD from Rio Grande do Norte. I think it's Samanau, the name of the project. And thank you for the suggestion. And I kind of forgot that I was going to talk. I got lost with all the information. But thank you for the suggestion.
I have a question for you. Where are you using LoRa? And in which frequency we intend to operate?
We are currently allocating it, but I think the uplink is around 401, 403 megahertz.
You know that this frequency is crowded, and you understand that you can have, and probably will have a lot of problems with regulation. Isn't it?
Yes.
You are aware of it.
Yes.
Any other questions? So,
Well, thanks. Yeah. So I'm not a RF engineer, but so since I understand that it is new to do this, that you want to do this communication with LoRa, did you do any preliminary link budget to know whether it's feasible already or not?
Yes, we have done both for uplink and downlink, and we have established a few parameters that will be used here. But this was more of a link budget for the CubeSat, not the PCD or the GST. But we have done that, and we have an idea of the key parameters that we need, both for the antenna, the uplink antenna, and the satellite antenna.
So, thank you very much.
Thanks. Desculpa. Aqui.
Open source framework from University of Minas Gerais is here. No. So we have here Kaiki for development of automatic application.
Bota aqui. You too.
Okay.
Good afternoon, everyone. My name is Kaique Sales. I am a mechanical engineer undergraduate student at the Federal University of Santa Catarina. And today I'll be presenting to you the development of an automated application to collect and filter CubeSats data.
Undergraduate students or graduate?
Under. Should I point you here? So we'll be going through the introduction, methodology, implementation, results, and then the conclusion. So we'll be talking about the nanosatellite FlipSat 1. So basically, for this project, I chose this model to work with because it was launched in 2019, and we already have all the data the satellite could give us. And also, I work in Space Lab, so I had easier access to the data of this model. So basically, what we are looking at is the overall diagram of the project. So basically, we got all the data that the FlipSat 1 sent to the ground stations around the world. We collect this data. We build an automated code to collect all the data and then send to a database. We call it raw database because the data wasn't filtered yet. Then we created another code, another logic to then filter this data and feed to another database. Afterwards, we got this data and feed to a website and a mobile app. So what were the objectives for this project? Nanosat Track serves as a platform with the primary goal of making data generated by nanosatellites accessible to the general public. It achieves this by offering a website equipped with interactive dashboards. So from these main objectives, we divided it into 4 other sections. Create a solution to automate the process, build 2 databases, the raw one and the filtered data one, then build a platform, the website, to show all this data in the forms of dashboards, and then finally build an app, a mobile app, to make it easier, the access for everyone, not only the missions team, but also the general public. So going through the methodology, we did build the development stages for the methodology. Firstly, we went through the literature review, then we started doing the FlipSat 1 data analysis. This took a while because we had some problems with the data collected in this mission. So then we went to the data selection. That's where we actually decided which data we would be working with, because we got many data sets, but not all of them were interesting in this project. Afterwards, we did the client-side and server-side diagrams. We started building what we wanted to have in this project. Later, we actually got to build the client-side development and then the server-side, and finally we got the final result, the platform that I'm going to show you later on this presentation. So in this research, we did read a lot. We got the access of many related works that was really great and helped us a lot to build this project. Some of them are the easy access to satellite data, the FlipSat 1 mission, GoZoo's mission, the Alpha Crux. That's a really great project that helped us a lot, and the CubeSat communications. So I guess most of you are familiar with this project. Many of my colleagues have already talked about this project, but basically we were working mainly with the OBDH, TTC, and EPS data. So this is the example of a beacon data of the FlipSat 1 mission. Many data, you can see some of them are the date of each data set, the temperature of the solar panels, the batteries, and many other modules. We have some current, voltage of many modules. We did a data selection because we couldn't get all the data and build a platform with everything that we had. It was too much data to work with. So firstly, we decided to build a beta version. And for this beta version, we selected this data. So we worked with the beacon downlink to be more specific. And then we tried to build the server side. This is the server side diagram. We divided the server side for this project in controllers, models, routes, and data. Each mission will have a controller, a model, and a route for each cell. So for example, we have the FlurryPassage1 controller, the FlurryPassage1 model, and the FlurryPassage1 route. And we would also have the Golds-Ufsky controller, models, and routes. So the client side, basically we divide it into public, folder, source, package, node modules, and many others. And then from the source, we were working with Reactive and React Native. So we divided the source into assets, components, scenes, and states to work with the API. Okay, now talking about the implementation. We choose to work with the MERN stack. So for our database, we thought it would be easier to use MongoDB as it's a NoSQL database. It made sense for our project since we had a lot of data and we didn't need to work with a SQL database that we needed to have some problems with structure and things like that. So one interesting thing is that we tried to work as a data-driven structure. What does that mean? We got the data from FlurryPassage1 and all the work from the first thing that we did this research to the final project, we always were aiming to have the best data-driven project. So everything that we choose and everything that we decided to do in this project was thinking about the first data that we had from this project. It's important to say that each mission has a separate database following the same structure. About the server side, again, we were using the MERN stack, so we used Express and Node.js. The controllers handled the HTTP requests. The models were defining basically the data structure, and the routes were working with the endpoint server response. Same thing about the client side, MERN stack. We used the library, React library, and the routes were working with the endpoints. That's the most exciting part, the results. So if you guys want to see the results, you can actually scan this QR code and we'll send you to the Nanosite Tracker platform. That's our beta version. So we do have some data in there. And if you want to scan it, you can do it right now. And I will go through this platform with you in this presentation. I'm going to give you maybe 5 seconds. How much time do I have?
8 minutes.
8 minutes? Okay, that's enough.
Including questions.
Okay. So, okay, so a little bit more time. Nice. So the first page, basically it's a Nanosite Tracker main page. This is a simple page. We only talked about the projects, what Space Lab is doing, the FlurryPassage1 mission, the Golds-Ufsky mission also, the Catarina A1 and A3, basic stuff. So if you click in the left upper corner, you can get this sidebar and you can go to the FlurryPassage1 main page. There, we actually talked about everything that's going on in this mission. Again, simple stuff. I think most of you already know the EPS project, ETC, OBDH. That's not what we are interested in talking about in this project. So then we go to the downlink. Here we have all the downlinks that we got from the FlurryPassage1 mission already filtered. So basically, we got many connections, but not only from our team. We gather information from many ground stations around the world, many ham radios, amateur radars from around the world. They helped us to collect this data. And if you guys are opening in your cell phones, you can see that's the filtered data. Then we got this data and we started thinking about, okay, so how can we transform this data in something useful? you can really see what's going on with your satellite only looking at this dashboard. That doesn't really make much sense. So then we filtered the data and we did create these graphs. Those are interactive graphs that show you the solar panels data, basically current, voltage, temperature, and things like that. You can select by the dates, and you can see everything that was happening with the solar panels. Same thing about the batteries. We have a batteries page. This is really great because when we are studying the thermal analysis, you can actually now check everything that we did in the ANSYS analysis. We can compare it to a bench test that we did, for example, in Leach. And then afterwards, we can get this data and compare it again. So now we have 3 different graphs showing you what should be the same data. And you can compare what was the reality of your CubeSat in its orbit with your test results. This is a graph showing you all the ground stations around the world that actually got connected with our CubeSat. So we had a ham radio in Japan that got a connection, some in the US, Germany, France, and Belgium, and many others. So there you can see where those ham radios are actually located, on where this data comes from. We also do have a page that we like to thank all the ham radio that does help us, because if it wasn't for them, we couldn't have all this data. So it's really important to have this connection with them. Okay, now going to the conclusion. Basically, we got that the NanoSat tracker has achieved more accessibility and visibility for the CubeSat telemetry data. What we wanted in the beginning was not only to show this data for our Space Lab team. We wanted to deliver this data in the easiest ways as possible to make it viable to anyone in the general public to have access to the CubeSat data. Using the MERN stack, the project provides a user-friendly platform. That was also one of our goals in the beginning. And at the end, we got the positive feedback from the Space Lab team. So we did got a user-friendly platform, and also the developers did enjoy the platform and got some useful info. Thank you, everyone. And this is my contact. Again, thank you.
You also are very talented young man.
Thank you.
And shows only the quality of the students of the University of Santa Catarina. So, questions? Guys? Questions?
Hello. So each satellite has different telemetry, right? Things change always. I think there was never 2 satellites I worked with similar telemetry. So how do you handle this in your system?
That's a great question. So that's actually something that Professor Bezerra. So that's a really great question. That's something that Professor Bezerra actually was worried about. So right now, that's the beta version. So we are only work with the Floripasat 1 and Floripasat 2 platforms. So that's much easier for me to collect the data and filter it. But we are trying to find a way to have a standard data structure to work with more satellites, because I don't. The reason we built this project wasn't only for our projects. We actually wanted to build an open source platform that anyone, any mission around Brazil or the world could use this platform and collect its data. So we still have this problem, but we are aiming for the second version to have a restrict structure that will make it easier for many other projects to work with. That's a great question. Thank you.
Other questions?
Very interesting work. This is the final result of a mission, when you can see this. My question is, the payload, if I'm not mistaken, was to test the subsystems and So, right, so these are the data that you showed are the data for the subsystems, right? So
It
it's,
is, it is.
it's the data for the platform as well as for the payload. Okay.
Yes.
Okay.
So, any other question? No? I have a question about cybersecurity. What do you think about cybersecurity? How you protect your system?
So that's a great question also. So basically, we did divide our platform into two databases. The first one, it's a more restricted one. That's the raw database. So basically, this one, for the first project, the beta one, we didn't give the access to everyone. It was mainly only the team, because we are collected everything that satellite has of data. So some of the data is sensitive, but then for me, I think we answered this problem by creating the second database. So after we got the raw database, we actually not only filtered the bugs, but we also filtered the data that we didn't want to expose to the public. So that's the data that everyone has the access, the second one. That's the filtered one.
Good one. Thank you.
You're welcome.
Thank you very much. With this, we finish the section. So thank you to all the presenters, session. And thank you to the chair, Professor Flores. And now we're starting session 4. And the chair is
Okay, so hi again. So welcome to session 4, Embedded Systems. And so the first presentation will be a base model architecture system for CubeSat development. So, welcome.
Vira só colocar o microfone aqui na bolinha. Obrigado.
Meu nome é Thiago.
Thiago.
By Thiago. Okay.
Só apertar. So, hello everyone. My name is Thiago. I'm from Federal University of Juiz de Fora, and I will present the work, a base model architecture system for CubeSat development. So first, we'll provide a brief introduction, followed by presentation of the methodology used. Then we'll show you the results and the conclusion. You see that we have a different approach, focus on education and academic satellites. So this project was developed by Supernova, a student competition team in the field of rockets and satellites at the Federal University of Juiz de Fora. Currently, Supernova is affiliated with the newly created LAPASCO, a laboratory of aerospace propulsion system. So the first academic satellite developed by the team was Imbaúba, which aimed to study the propagation of ozone hole from Antarctica to Brazil. Through this project, we saw the importance of the knowledge management system and a project methodology, especially for academic teams. Thus, we developed what we call a base model architecture. So the base model architecture is a methodology that divides the development into 3 blocks. We have the application block, which is the specific requirement or component. Basically, by defining the system requirements, we develop the firmware and hardware separately for each application or module, and we can make a bench test or not. After that, a set of applications is used to assemble the subsystem. Finally, a set of subsystems form our project. So the idea was to use what we call a base model architecture for developing a multi-mission platform aimed to enable knowledge management with the team and facilitate the future development for new projects. Now we'll talk about the development of a multi-mission platform using this methodology, focus on each subsystem. So the electric power system is designed to supply and distribution power to the satellite. In general diagram, you see how our EPS is divided, with power generation, the solar panels, storage, the batteries, control and regulation. The hardware was developed by the team. Basic requirements were considered to safely supply and power the mission platform. We have 3 voltage levels, 3.3, 5, and 12, and 20 volts. The battery duration follows the competition regulations. The focus on maintain the low DOD. The onboard data handle, process, encode, and verify all data generated and received by the satellite. As system requirements, we have communicate and command all microcontrolled subsystems, manages all data, responsible for telemetry operations, and communications directly with the payload. So here we have the general diagram of onboard data handling, showing the protocol used and the data and comments sent and received. The attitude and orbit control system was responsible for controlling and pointing the satellite. He has the system requirements: communicate with OBDH, receiving comments and sending data, drives the motors for reaction wheels, collect data, collect satellite operation data, and deploy the antenna. Again, we have a general diagram of AOX showing the protocol use and the interface with some sensors and actuators. The telemetry tracking and command is responsible for the communication interface between the satellite and the ground station. The antenna was designed for 50 kilometers transmission. The operation frequency is 900 megahertz. It has the ability to send and receive comments, and the communication interface should be able to communicate with the Mach 1 supervisor system, which is an open source human machine developed by the team. Human machine interface developed by the team. The structural design, we do not attach the structure itself, but the PCB, which should respect the dimensions of CubeSat. The boards should have the same dimensions, and the payload may have the half of the size. This is defined by the table and the figure. The payload should be a simple mission executor, without needing to provide information or act in the way to ensure the spacecraft survival. It should respect the size defined by structure design and communicate with OBDH over WART protocol. So talking about the results. As a result, we have the Tupã project, a 2U academic CubeSat with the mission of lightning detection. Here we have some characteristics and photo of the first integration test. This was our first engineering model. The satellite was built for IMP Challenge, the cube design, and has mission in two parts: identify the centroid of lightning in a sequence and identify the time of occurrence of lightning flashes. For this, you use a camera communication with Raspberry Pi, which uses the OpenCV library for data processing. As conclusion, we achieved the knowledge management. We hope that implementation of the base model architecture enhances knowledge management, and it allows projects to be comprehensively understood on an application-by-application basis. We have continuing improvements, so we have some ongoing improvements primarily focused on structural design, the AUX OBDH loop, power regulation and distribution, and thermal control. For future plans, we expect to bring this project to Spaceport American Cup, an academic competition of rocket design and satellites. So with this, I conclude my presentation. I would like to thank you all for the attention and open up for questions.
Thank you. Are there any questions?
I actually have a question.
Yes.
What type of, how did you guys did the lightning identification process?
The lightning identification process was made using the library OpenCV. So we had a camera on the satellite and connected to a Raspberry. And using this OpenCV library, we apply some filters on the image, and we identify the centroid of the lightning.
Okay. Are there any other questions in the audience? Yeah.
So I got very curious why your ADCS module deploys the antenna of your satellite. And what is the logic?
Can you repeat, please?
It's working. So my question is, why does your ADCS module deploys the antenna in your satellite?
Yes. It was, how can I say? Actually, it receives the command to deploy, and by the way we have the competition and what we want to achieve, we just do this in this form. Mm-hmm.
Thank you. Thanks. Any other questions? Yeah. Oh, yeah, there, please.
Please, this slide with the term the capability of the link of the system. It's writing the 15 kilometers. It's correct.
Yes, it's correct.
It's correct.
Mm-hmm.
It's my suggestion to you is to verify this link, because 50 kilometers I can use to test the simple link in the system.
Can you repeat, please?
Yes, this 50 kilometers is not enough to correct the link between the system.
Oh, it's an academic satellite.
It's an academic satellite. Well, so what's how to define this link?
This link. The responsible for this part of the project is not here today, and it's not a part of the project that I have all knowledge. So I can ask you first, and then I can answer you.
Okay, thank you very much.
Okay, thank you. Thank you very much. Diego.
Obrigado.
The next presentation now is investigating the impact of CubeSat size on power generation. It's by Gabriel.
Hello, hello. Okay, good afternoon, everyone. I would like to start saying that I am really happy to be here. This is the second time that I make part of the Latin American CubeSat workshop. In the first opportunity, I was presenting my undergraduating thesis, and now I am going to represent Professor Edemar. And the paper that I'm going to present is titled Investigating the Impact of CubeSat Size on Power Generation. It was research conducted by the NEST and Space Lab Laboratories. And I'm going to, yes, thank you. And I want to start showing the structure of the presentation. I'm going to start with an introduction related to CubeSats and the challenges related to the power generation when the satellite have the solar panels in its own structure. Well, I'm going to present the objectives behind the research, the methodology used, some models that we had to use to make the simulation, the results, and some key takeaways. Okay, so I'm going to start with introduction of CubeSat, just to contextualization, and then I'm going to talk about the challenges behind the use of the solar panels in its structure. So I believe that everyone here is already familiar with, but the CubeSat is a standard created in 1999, and we have a specific unit that should be of edges measuring 10 centimeters and no more than 1.3 kilograms. Today, I believe that is 2 kilograms. Larger CubeSats could be developed using more than one unit, right? Bigger satellites could be developed, 12U, 27U. But when we use this type of satellites, we are considering that, well, normally, it is a project with a lower budget. So we are not going to have, we won't have any mechanism for deploying more solar panels. We are going to connect the solar panels directly in the structure. So furthermore, we have some limitations related to the attitude control. Normally, we won't have any type of active attitude control. We are going to work with some passive control, right? So these limitations start to reduce the amount of energy that we can generate for the satellites. So when we do our mission, when we concept our mission, we start to, it is necessary to define or estimate the power that we are going to have during an orbit, right? So what are our objectives? Well, first, we would like to estimate the power generation capacity for a given orbit. We would also like to simulate different sizes of CubeSats. We would like to see how much power a CubeSat, a 1U CubeSat or a 6U CubeSat would generate during an orbit. But I believe that another objective was provide more independence to the laboratory, eliminating the need to use third-party softwares or something that we don't exactly know what are doing behind the scenes. So, what were the methodology? We had to consider some models for the solar panels, for the attitude, for the orbit itself. So I'm going to start with the solar panel. We considered a relatively common equivalent circuit of a photovoltaic cell. The idea here is that we have a current source in parallel with a diode, and the series resistance account for internal losses due to current flow, while the shunt resistance, which is parallel to the diode, represents the leakage current of the panel. So, I'm going to say that in the paper, it is described how we get to the equation here, that we can use an iterative method to resolve. But what is important here is that the radiation flux and the temperature are the inputs that we use to make the simulation. We had also to take some considerations related to the solar panel that we are going to use, some parameters. So it is important to highlight, for instance, that we imposed a constraint where the voltage generated by the solar panel is fixed at 70% of the open voltage, open circuit voltage of the selected photovoltaic cell. We have more information here about the model of the PV panel. And to account for each side, because we have equivalent circuit for one solar cell in that case, to simulate for different sizes and even to modify the inclination of the satellite, we have some multiplications to account for that. So in 1U CubeSat that we have only one panel in each side, we don't multiply. But for a 6U, where we have two sides with 6 panels, that we are considering that all the sides are composed by solar panels, we make the multiplication by 6. The other two sides that have 3 panels, 3, and so on. Other considerations that we used for the simulations is that we are using a circular orbit for the simulations, an altitude of 500 kilometers was used too. It is a a relatively common altitude adopted in CubeSat-based satellites. So it is a good start. A nadir attitude was imposed. So the same CubeSat side is pointing to Earth through the orbit, and an inclination of 90 degrees was considered. So I'm going to start talking about the results that we had with all these considerations. What I can say is that for all the situations, we have this solar irradiation characteristic for the sides, all the 6 sides of the satellite. So what will change is the number of solar panels. So here we have the results for 1U CubeSat. And another thing that we are going to see is that the inclination, the orientation of the satellite will change too for the 6U CubeSat. So it could also change the power generation during an orbit. Here we have the profile of the power generation by a 2U CubeSat. Here we have for a 3U CubeSat. The profile maintains relatively common characteristics, right? They are really similar until now. But now we are going to start to see that the profile changes a little, and this is for a 6U CubeSat. That the bigger change happens only in 2 sides of the satellite, and this changes a lot the geometry of the CubeSat. 6 times bigger than a side of 1U CubeSat, 2 sides. So now this is also a 6U CubeSat, but the orientation is different. So we have an average a little lower than the previous one, just because of the orientation of the satellite. And then we have a 12U CubeSat, also showing a relative common profile. And for showing all the results of the CubeSats, we see primarily these 2 ones, a profile really different than the others, right? So we have the average power generation for each CubeSat. I think this value is wrong. But the idea here is to show that the increase on power, it is not linear, right? And we can see that we can have changes just because of the orientation too. So I believe that some conclusions here that we can do is that the CubeSat, as expected, when we use the solar panels in the structure of the satellite, when we have a bigger satellite, we are going to have a bigger possibility of generating more power. And another thing that we could do for next steps would be comparing, selecting a lot of considerations, and using other softwares with these considerations as input to compare the results from each software. Another thing that we could do is considering real mission data to compare to the results that we are going to receive from each software, right? So there are references, and thank you everyone. I'm going to try my best to answer some questions if there is any. Thank you.
Thank you. Time for one question. Anyone who wants to fire? No? So I had one is you build that model, but you have also satellites in orbit where you have this data, like the presentation we saw before. Were you able to correlate your model and real data that you have?
Yeah, I believe so. In fact, I think that could be something that Professor Edemar could add to the work, for instance, or next steps for comparing and making this correlation.
Okay, great. Obrigado.
Thank you.
Okay, we can close the presenter once more. Thank you. Now we will move to the next presentation. So it's titled EPS control for CubeSats.
Você colocar aqui. Aí. Okay. So, good afternoon, everyone. My name is Vinicius, and today I'm going to present my work, EPS Control for a CubeSat. It was my course conclusion work, so it's very shortened, but I think it will be good anyway. So, it was supervised by Professors Maria Cecilia and Patricia Pena from UFMG. First of all, let's talk about the CubeSat in question, the PDQ-SAT or Pão de Queijo satellite. It's an academic CubeSat that has been in development in the Federal University of Minas Gerais, UFMG, in partnership with the Brazilian Space Agency. So the main goals of this mission is to test and characterize two components, a commercial lithium sulfur battery and a handmade supercapacitor in the space environment. So we can know if they are suitable for those, that environment in specific. And by doing that, we are qualifying the aerospace engineering students because all of the work done in the PDQ-SAT project is done by the students. So we are working on that goal as well. So for this work, the goals actually focus on the EPS, and it's a continuation of another project that has been developed in 2022, in which we worked on making models for the EPS, for the operational modes of EPS. The battery used in the payload, the lithium sulfur battery, is going to be tested in a charge and discharge type of process. And by doing that charge and discharge, we're going to see how it reacts in different values for the maximum and lower charge limits. I'm sorry, I'm very nervous. So we are going to also use the lithium sulfur battery, the payload battery, to donate some energy if the satellite needs it. So the satellite is going to go around in its orbits, and if the energy that it has, it's not what it will need to complete the orbit, the lithium sulfur will donate some of its charge to them. And then we're going to integrate those models with the ones that were developed in previous works. Then we're going to synthesize these models in supervisors from the supervisory control theory, and then simulate the supervisors to know if the actions that the supervisor will implement are in meet with the requirements that we will establish. So talking about the theories used in this work, the discrete event systems that are independent of time to happen, they can be represented by the automata, that is the image over there. And it has some states and events that will transition from one state to another. We can then compose, it's like a sum of automata into supervisors that can be used to reach a specific path that the user wants it to happen. So if we get the global plans and the specifications of that system, we can tell to the supervisor, and it will make so that even with unexpected events in space, we can reach a wanted path in the system. For the simulation, we use some orbital mechanics formulas, equations, like the Kepler's equation, to know exactly where the satellite would be in a specific time. We use also some procedures of battery management systems so that we could improve the quality of the battery models, like controlling its battery charge, discharge, temperature, and state of charge, the value of the charge in each instant, so that we could reach a more reliable system. By doing so, that interface between the lithium sulfur battery from the payload and the satellite bus battery, which will charge all of the systems, we can assure that there is an alternative way of the satellite for charging if it cannot be in the sun for using its solar panels. So this is the first modeling of the satellite that has been done in the work of Santos. The previous work that also was about the EPS modeling. In that work, Santos developed 3 supervisors, one for the solar sensors, for the satellite to know if there was radiation from the sun reaching the solar panels. A supervisor for switching between the satellite power supplies. So if the satellite was in the solar region, there was no need for it to be using the battery charge. So it would change to the solar panel supply power. And a supervisor for the EPS operating modes, that are this one. You can see in there the 2 plans used to make the supervisor. The first one was of the operating modes itself. There was a normal operating mode and an emergency operating mode. The difference between them, it was that in the emergency mode, the satellite would shut down some of its functionalities to reduce the charge utilization by half. And below we have the other plan that would tell if the state of charge of the satellite battery, the one from the bus that would charge all the systems, if the battery was above or below the 25% charge. That was the level that Santos chose to be the limit between them. And by composing them into a supervisor, he reached this supervisor that did actually change in the simulation according to what he was expecting. So for this work in specific, the path followed was the same as in the work of Santos. We started by modeling the plans, specifications, define the requirements for the system, what we would want to happen in the system. We use the UltraDES software that is from a laboratory at UFMG. Then we integrated these models with the ones developed by Santos, simulated those in a environment similar to what would be happening in space using MATLAB, and then analyze if the actions that the system took during the simulations were according to what we would want, what we can see there that we established that the batteries would be 2 packets of cells, battery cells, that would be passing the charge from each other. So you can see there was a main battery in which the tests would be happening. So we would measure the current voltage on the main battery, and the secondary battery would just store the charge that would not be used anymore in the test. So the first model, the first plan showed in here, says that for each state, the secondary battery would have more spare charge to donate. So we would start at the state 0, and then after the first stage of test, the cycling would not need more charge, and you could donate 10% of its charge to the satellite if it was needed. So we would move to the second state that it says in there 10. And then we go up until the end of the test. And so we needed to know if the batteries were up to donation or not, such as in the satellite needed already some charge, and we need to know if the lithium sulfur batteries still have charge to donate. So we created another plan that would say if the battery spare charge existed or was empty, so the state's empty or leftover charge, and then passing to the operating modes. Differently from what Santos developed, we created a receiving mode that was exactly to this donation from the payload to the satellite. And this was the new supervisor that we came up to. For the simulation, we defined some aspects to the orbit, to the variable, so we would know at each step of time how much power the satellite would be gaining or expanding, to know how it would be in the next step of the simulation. And here is a graph only showing the test. You can see that the bottom limit is how much charge it would have to donate, the lithium sulfur would have to donate to the satellite. And these are the percent of the charge, and then reaches a state above the 25% and enters in the emergency mode. But why does not enter automatically in the receiving mode? It was because in the first stage, there is no charge to donate because the battery is using all the charge. So it would have to wait until the batteries have charge to donate and then enter the blue phase over there, in which it would be able to receive some charge from the payload. So in here, we tested some extreme conditions to know if the satellite would survive with this new functionality. And we can see that in the first test, it was tested if the battery lost more energy around the orbit. The second case was if the emergency mode didn't work. So as I said before, the emergency mode, it would shut down some of the satellite's functionalities, so it would save more energy. So if this wouldn't work, the satellite would still go up the mission. It would not fail or reach a state with no more energy. And we tested also a case in the solar panels failure. So if the solar panels, not all of them, I think 20% still would be working, but we can see that also the satellite could go with the charge from the donations, but in a variation much slower, much shorter than the others, reaching just above 40% of battery. And with this, we could get the behavior we wanted. The cases tested were show us that this new mode would allow us to reach some extreme conditions in the sport test. The plants were generated and functional as well. But the limitations encountered was that there aren't much works about the use of discrete event systems and satellite design. So it was a lot more difficult to find how to model some things and how to create a plant or a specification that reaches some specific behavior. And because we still don't know much about the batteries used in the payload, the variation in the charge along the steps in simulation were kind of arbitrated. So this doesn't show exactly what would happen in a space environment, but I think it still were good results. So thank you.
Thank you very much for the presentation. Time for questions. Yes.
Congratulations for your presentation. About the discrete event system, what kind of tool do you have using to simulate that?
To simulation?
The events. Can you back 3 or 4? For example, like this.
So in the center simulation, he created a kind of orbit using this aspect in which the satellite would start at the right side of the Earth in a shadow region. And then as it reached the solar, it would start to chart up. So in MATLAB, he made a not complex line of code using just if statements. And since the simulation is discrete, he could do it just like if something happens, the new state of charge of the battery, it will go up this much. And then it will repeat itself until the end of the simulation. So it was only if statements using the values that he prepared.
Do you know a tool called color patternets or patternnet models?
No.
I suggest you to make a little research about this because it's a very useful tool to simulate discrete event system. Color patternets. Okay.
Okay. I'll research about it. Thank you.
Okay. Thanks again. I think we are running. You want? Okay. One more question.
Hello. It was a very good presentation. So I was just curious about the battery management system, and my question is, it's a commercial one or you guys made one?
The battery management sense.
Yes.
So the PQ sat it's still in the project phase, and we are still developing some tools that we still don't know if it will be used in the real satellite. So we still don't have any physical battery management system. We just use the concepts to create the models, to know what we would be analyzing, and for time that's what we have.
Okay, thank you.
Okay, so let's thank again our speaker. Thank you. Last presentation.
Techniques to radiation. So we will have a little introduction about radiation and the research of radiation on Space Lab. And then we will talk about the component selection criteria that was used on the project. And then we will have a little look on the highlights of the project and some of decisions and lines that were made during the development. So radiations are a very concerning problem on space applications, and it's becoming even more concerning because CubeSats are starting to have more complex missions, and their time on orbit are starting to increase. So here we have an illustration of a single event burnout occurring on the die of MOSFET. And here an illustration of the Van Allen belts. We have three main sources of radiation. There are cosmic rays that comes from outer space, and radiation belts, that the Van Allen radiation belts that occur because of the Earth's magnetosphere, and solar flares. So in Space Lab, we are conducting a research that tries to do some experiments with the red hard components. This is the latest one, the payload XR. It combines a SOC FPGA and a microcontroller to do on-orbit configuration experiments. And this work is about doing the next generation, which involves developing a new computer for doing on-orbit processing. And the idea is being something more robust and having more capability to work as a payload or onboard computer. So let's talk about the component selection criteria. As everyone know, in federal universities, we don't have much budget, so we can't allow ourselves to test every single component. So we develop some strategies to better select each component. So the first one is the development of a method to prioritize the components that we have tests of total ionizing dose and single event effects published by other agencies like NASA and ESA. And then we use the TRL from NASA to start somehow give a classification for the reliability of the component. Another technique that we used was derating, the idea of finding the maximum allowed value for the components, like the capacitor or resistor, and symmetric like the voltage, the maximum allowed voltage, and we use the factor of 60, for example. That will reduce the stress and somehow will reduce the errors. So now let's talk about the project development and the case study analysis, the project itself. So some initial considerations, the SOC is very huge and we have a lot of things going on the board. So sometimes we prioritize the space rather than some reliability choices. And we also try to, where it's not much critical, reuse some circuits that were used for the development kit. For example, the circuits responsible to manipulate the SOC and the loading bitstream on the system. And of course, we use the rating and TRL techniques that we explained previously. And since we don't have a mission yet, and we didn't use any orbit to try to predict cross-section or anything like that. So we used the SOC specifications, which are here, 50 carads for the total ionizing dose and single event effects above 65 megaelectron volts. So the processing system, the SOC that we are using is the NEG Ultra SOC FPGA. It's a very robust SOC. It uses a lot of features to try to mitigate effects of radiation, like the embedded EDAC for memory, also scrubbing, checking of the integrity of the bitstream. The bitstream is stored on 3 different memories, and we can correct single event upsets using triple modular redundancy. And also for the volatile memory, we have a Reed-Solomon encoder. It's very hard to see, but it's a red hard SOC, so we won't have to deal with any problems from the SOC itself. The challenges will come with the costs that we're going to choose for the project. So let's start talking about the processing logic, the things that are connected to the fabric. We have a sensing system. Since we want the possibility to this board to work as an onboard computer, it has integrated a magnetometer and gyroscope that can allow for some simple attitude control. It has an ADC with that allows for analog for reading of analog pins, and has a lot of interfaces like SpaceWire, CAN, and has some generic pins like the one for LVDS, which is differential, and one simple, generic. The channels for the ADC are externalized, and also some wide channel for testing. For the sensing, since we adopted some node isolation technique, which involves isolating all the components from the main bus in case a fault occurs. So if this component fails, for example, we have an option to turn it off from the bus. The memories. For the memories, we choose different combinations to balance between the features of reliability, capacity, and speed. We choose an eMMC that has a capacity of 128 gigabytes that can reach up to 400 megabytes per second. And with this, you can, for example, run Linux and store lots of data. We have MRAM that is very robust and is very hard to occur any single event effects. So you can store any critical data. We have a group of NAND flash modules that work in triple module redundancy of 4 gigabits that can mitigate single event upsets. Now let's talk about the power system. For the consumption estimative, we used the tools provided by the fabricant, and we estimated an application that uses 75 to 80% of the resources. Is a lot more than we expect for the projects on Space Lab, but it's to give a good margin. And for the costs, we always choose the worst cases for power consumption. And we got all the rails for the alimentation and its consumption. So with this, we also added loaded protection for single event latch-ups. Here are some simulations. We are using the very used LTC 4361. And we are using many to protect the components that we founded through the research that were very sensitive to latch-ups. Here is I don't know how much you can see here, but we have the automatic retry. After the latch-up, it waits 130 milliseconds to turn on again. We can see the current spike and the voltage spike. They are protected. A little bit of the voltage on the alimentation bus still goes up, but thanks to the rating, it's not to be a problem. Here's some information about the alimentation of the SOC. It uses the LTM 4690, which is also has flight heritage. And in its worst case, its efficiency is at 80%. Here is the main supply for the DDR and the SOC processors. Its efficiency stays at 83, 84% at the worst case scenario. Here is the efficiency curve. It also has flight heritage. And here's the final power cascade for the whole application. The whole thing comes from a 5-volt power supply in 3.3 and gets converted eventually to the FPGA and to the SOC. Their core are always alimentated with 1 volt and their supplies are isolated. The the ultra supply also needs 1.8 volts for the socket, and we have some reference voltage for DDR, for example. Conclusion. Here is an overview of the board. It's very hard to see, but we have the sensing buses that have sensors of the temperature, and we have the memories and everything else. Here, the color indicates somehow the TRL system that was adapted to somehow quantify the reliability of the project. For the next steps, we are going to do more. We're starting to be doing some simulations and starting with the physical layout design. We also, since we used some of the parts of the dev kit, we expected to have some parallelism to work with start working with firmware as fast as possible. And the future mission expectations are the Persistent 1 and Rockus 1 missions from Space Lab, and maybe it can be used for future deep space missions. And that's it. Thank you very much.
So, any questions? Yes.
Thank you, and congratulations for your nice presentation. I have two questions. The first question is about if you have had some problem, for example, from lead time for some component to receive or to buy that. And the second question, if you are using kind of protection for external memory, for example, like error correction code, you even software. Okay, thank you.
We know we're still not developing, buying any parts because we're still developing the physical, developing the PCB itself. This work is just about the architecture, but we know we probably have some problems with this. The socket is not very easy to get, but yeah, the second question about the error correction. Yes, we have a lot. The SOC has a lot built in, and you will probably add some more with our own development of software. For example, there are a lot of memories that work in TMR, for example. So we have to implement error correction, and we can, of course, we can add more things like Reed Solomon, for example, on our own parts.
Okay. Any other question? No questions? I have many, but I was just going to do. But it was very interesting to hear about this and see that you were considering so much radiation. And what is the comment? So it's nice you have the rating, and this can help. Just be careful because for power MOSFET and so on, 75% is not enough. It's the rating for triple-E reliability. For radiation, you need to add more. So for some high-risk mission, in ESA, we recommend to derate to even 30% BDS and 50% VGS. Okay. So as a minimum, and it's no guarantee because you can have one of the effects, which is gate rupture, for which the rating doesn't really help. So if there is one of the things that you can test, it's like the power MOSFET is one of the good components to check or have a radar run, or if you can. But derate more, much more. So change that. Then you said that you're using this FPGA, Ultra. Yes, Ultra is good because it's not that chain, and
the CRAM is flash-based, so like all flash-based FPGAs, it will have no errors on the CRAM. But it can still have errors on the flip-flop side and things. So it's not completely immune, and you need to just consider whether or not it can be an impact to have errors on the flip-flop, and whether you're doing something for that or not. Okay, and the last point, and I will stop here, but there are some other points, is these FPGAs, they need to have a very high tolerance to on the power supply. And usually the margins are very small for voltage excursion. So be careful of the possible transients that you can have on the power components that can create some increased spikes on the FPGA. So I would recommend to really put some good filters as much as you can to avoid these spikes on them. And the DC-DC converters also you need to derate and avoid those with power MOSFET inside. And then I stop. Yeah, but thanks for
For the switching converters, I use the safe operating area from the works.
If you have them, then, then it's good to use in the input voltage and the output current.
About the MOSFETs, I also look to lower the ratings, but we still have a very problem with the space. Because if I lower, I'll probably need a bigger MOSFET. Yeah. But I'll sure look into it.
Okay.
And also the flip-flops.
Okay,
Thank you.
Any other questions in the meantime? Okay, thank you. Let's thank the speaker again. So now we have questions whether the person who is going to present the next presentation is here. So the title is Maximizing Power Potential, Designing an Algorithmically Optimized Solar Cell. Something. Is this person present in the room? No. Okay. And the next presentation is Strategic Framework, Developing Effective Test Plan for CubeSat Electrical Power System using ECSS and mission-specific methodologies. Anyone in the room? No. Okay. So we go to the last presentation, which is quadruple antennas for CubeSats. Radiation characteristics in different configurations and initial results. It's you. And it's Junior. Yeah. Okay. Okay. So the floor is yours.
Qual seria o botão? Okay, good afternoon or good night. I am Junior. I am a master in electrical engineering student, master in student in electric engineering in USC. I am an engineering in telecommunication, and I want to present to you the work named quadrupole antenna for CubeSat radiation characteristic in different configuration and initial results. First of all, I want to alert, maybe in my speak, I have a little of Spanish, maybe Portuguese, and a little of English too. Okay. I can do that. Okay. First of all, here we have one graph with from this font. We have here the frequencies where the maximum the CubeSat are working from this font here. And we can see that the mostly frequency used in this and the CubeSat are in the UHF frequency, okay, bands. Then we have another frequency here, but in the I can say for you that the frequency in USF is the mostly uses for the telemetry and control of the CubeSat. Okay, that is the one detail for introduce this question. What is the mostly used antenna for UHF in CubeSats? What is the, well, that the answer is monopole, dipoles, and quadrupoles. Okay, many different configurations of these types of antennas. Okay. A quick analysis in the radiation, the radiation diagram. Here is we have one radiation diagram in 3D. We can see that here we have a little space where we have a low gain of radiation of this antenna. Okay, this is a little representation of 3D to do one idea. Sorry. To do one idea that the radiation diagram of the antenna. For this one is one monopole. Okay, this is the configuration. For our this little study, thank you. Okay, for this little study, we use the next antenna configuration and simulation setup. Okay, the antenna configuration study are these four. Okay, the monopole antenna configuration, that is a single radiation element. The second one is the dipole antenna configuration, that is two opposite monopoles, one in one side of the CubeSat, another in another side. In this image, we can see one monopole is one of these four, and the dipole is one in this phase, in another phase. Okay. The another configuration is the bidipole array configuration. Is two monopoles are arranged in 90 degrees in one in relation to another. Okay, and the figure is, for example, is this one and another one. Okay, 90 degrees. Is the another configuration is the turning style antenna configuration. That is the two dipoles antenna crossing in cross. Okay, in cross configuration, crossing two dipoles antenna. This here is the radio frequency model for the FloripaSat2 platform. Okay, in the top of the model we have the antenna model for the radio frequency simulation. Okay, that is one deployable antenna. This is a simplified model. The results of the simulation for the results this in the simulation we have here first the monopole. Okay, in the monopole results, where we can see here this little angle here when where we have a maximum of minus 15 dBs attenuation. Okay, this attenuation can be a little difficult, a little inconvenient for a budget with low with a low low flexibility, or maybe with one antenna in the ground station with a low gain, for example. In the another part, we have the more homogeneous radiation diagram, but is in 2D. In 3D, we have here a cone with some angle that can be have an influence in one area, maybe of one country, maybe one state. That is a little inconvenient for the Lincoln budget too. The another configuration that we have is the dipole antenna, that we have a little minor attenuation, but we have attenuation, okay? We have here in the simulation minus 12 dBs of attenuation. For in this occasion, we have the attenuation to sides of the satellite. That can be a little inconvenient for the mostly of the satellite that no have altitude control. The another configuration is the weird dipole antenna. This another configuration maybe is the little this configuration have no pole when the radiation diagram have a high attenuation. This configuration can be convenient for the mostly of the satellite without altitude control, but it have a low complexity for the implementation. That may be a convenient configuration. The last one is the turn-style configuration antenna, okay, the turn-style antenna that have the more homogeneous radiation diagram, but have the high complexity to implement, the more high complexity to implement. This here is the first prototype of the prototype, and now we have the first version and the flight version of that prototype. But this was the prototype that we measured here in Cimatec in the anechoic chamber. We have some results with this prototype. That is the experimental setup, where we have here the antenna receptor. Here is the CubeSat, with the antenna in the top of the CubeSat. Here is the experimental result. Is the first result for one monopole only. We have here, we can see here, this is the radiation diagram, but as for is normalized. We can see here the attenuation was maybe 30% of the power is attenuated in this part here. In this another part, we have a more homogeneous diagram. Remembering that is the two-dimensional view. In 3D, the radiation diagram can be different, but it's a little complicated to do that in an anechoic chamber, because So a lot of work, okay? Then the conclusion for the little study was that here is more for informate and do a little some curiosity to help in the moment of in the select one antenna for one CubeSat. The conclusion is the monopoly is simple, having only a coaxial cable fit for each monopole. Okay, the dipoles and bidipole have the similar complexity to implement. Needed a previous circuit to do the alimentation of the two monopoles. But the bidipole is preferred for the circular polarization with the more uniform radiation pattern. The turnstile configuration provides the circular polarization and have a highly uniform radiation pattern, but increase the implementation complexity and reduce the number of radios that you can use in the CubeSat. For you to radio, for example, you need to put two antennas in the CubeSat. Another conclusion is the monopole configuration has the more general conclusion. The monopole configuration has the most easily projects from the dipole and the bidipole. The bidipole become the preferred configuration before the circular, because the circular polarization and the uniform radiation pattern. And finally, the turnstile configuration become the best choice for more stable and reliable links. Okay? Então, that is the conclusion. Muito, very much thank you.
Are there any questions? No questions. Everyone is eager to leave.
Telecommunications.
Yeah.
That's a question if there are no.
Okay. But I don't think it's working.
Yeah. Yes, I have a question. What are the next steps in order to have this antenna flying in a satellite?
Okay, a good question. The next steps are, I don't know, because we have 3 fly versions being produced in the moment. Then the next step, I think, is testing the CubeSat. I think that's the answer.
Okay. And I have one question for you, Mr. Guevara. Who was your grandfather?
You say for my first for my first name or
Yes.
for the second name?
For the third name. Yeah.
Okay. It's
But
not,
it was a joke.
it's not that one, I think.
Well, gracias, obrigado. Bon, thank you. We can upload. You have one question. One question. More questions. We are not finished yet.
Hi, Junior. Thank you for the presentation. When Professor Bezerra asked about the next steps, what do you think about electromagnetic compatibility tests about the interference of one antenna in another antenna? Have you tried to think about that, or just an idea that
Yes, I have one idea. It's a good question. In the monopole configuration, the most recommended configuration is use one monopole in one frequency, very with a big difference of frequency one of another. Okay, for example, if you are using two monopoles, one in one phase, another in another phase in the same line, the recommendation is use one VHF and another UHF, because there are interference from one antenna with another. The mostly the problem that you can have in this configuration using the two antennas in the same frequency is that you can burn your radio in the another antenna, because it's the transmitter wave is receiving for the another antenna, and this can that can burn. Okay, that is possible to understand. You can burn the another radio. There are another question, but it's more in the communication protocol. When one is transmitting, the interference is not let the another radio receive the signals coming. For example, if you have one CubeSat, one antenna is transmitting in the same frequency, and another is receiving in the same frequency. This antenna is do a big influence in this antenna, and then you will not receive the package for the Earth, for example. But that can is that happen. That is the same situation if you have the antenna here. That is one study to do. But it's not the antenna the problem. It's more the radio and the communication protocol. The communication protocol in the physical layer.
Hi, good afternoon, no, good night, good evening. My question is about, you have obviously a system where you have a transceiver, a physical transceiver that's generating the carrier wave, and then you're feeding this, I think, through a coaxial cable to the antenna. What's the, if you guys think of this, and if it has some kind of shielding inside the CubeSat, so this signal that's generated by your radio does not interfere with the systems inside the CubeSat itself.
If I understand good your question, you are saying that the antenna is transmitting one frequency, okay? The frequency is clear, is a sinusoidal carrier wave, okay? It's not another frequency with interference. Then your question is that frequency have some influence inside of the CubeSat? Yes, that is that possible? But the CubeSat need be to projected to do protection for that frequency. Mostly of the circuits are protected for that frequency. For example, the transmitter are protected, the lines, the transmitting lines are protected, natural protected. For example, for one wave, interference, do interference in one circuit, he need to that wave need to that wave need to induce a current in this circuit. Okay, if for do that, this circuit need to be in 50 ohms. Okay, for 50 ohms, no, it need to be in the impedance of the space. Okay, then for that the antenna is good to catch this radiation wave and be converting in electrical signal. Okay, but the another circuits are in a big problem for that circuit. That if there are a little of a current induced in the circuit, but it's very, very low current. Then the circuit continuing working well. The mostly problem is the transmitting having another frequency more low interference, for example, in one oscillator or something like that. It's mostly the problem, not the frequency, the carrier wave. In my end, that is I understand. Okay, maybe there are one detail that I have no the idea now, the information now for you. Okay.
Okay. Thank you. One last question. And then
In fact, it's not a question, it's just an observation about his question. I think that he asked about electromagnetic compatibility issues concerning other boards inside the satellites. So he asked about what happens with the source, the RF source, if the RF source interferes with the rest of the boards inside the satellite. So there are some tests that we are going to make concerning electromagnetic compatibility, and those tests will ensure that the boards will work properly, even with this RF source inside the satellite.
Yeah, exactly. The circuits that are in the satellite pass for those tests in the moment of the project. Okay.
Okay. So with that,
thank you
again to the speaker. And thanks to you two who all survived today. And with that, we end today. Professor Desan, you have something to say?
Thank you to the presenters. Thank you to the chair, Dr. Dias Gupta. Thank you to everyone. And tomorrow at 8 a.m. we have the industry session. Very interesting for the ones looking for a job and for ones looking for products for your concerns. So see you tomorrow. Yes. So we are back to the first room where we were this morning. Tomorrow we did the whole day in that room. Yeah, second floor. Okay, thank you.
Vou parar aqui então.
Muito agradeço.